learning experience. Hope to see you in class.
I suppose the first thing I could say is that you should take this course because energy and climate change are going to be the biggest issues of the 21st century. That's big with lots and lots and lots and lots of exclamation points. I could go on and explain to you that, demand for electricity is doubling every 25 years. China is building a new power plant every week, and this is putting tremendous strains on our natural resources and our environment. I could also talk to you about the threat of climate change. The United Nations has reported that the temperatures are going to be increasing over the next 100 years, leading to more erratic weather patterns, higher sea levels, and all sorts of changes in our natural environment. The problem with taking this approach is that really I would just be perpetuating a lie. Well, if not lie, just a whole lot of hype. So the problem is that the media loves a big story, and I think and activists love getting your attention, and so those two factors combined lead to sort of a lot of exaggeration about the actual consequences of our energy future and the actual consequences of climate. So take that fact I just gave you, right, about how the electricity industry is doubling every 25 years. The point of this class is to sort of take some basic economic tools and use them to sort of enlighten just what, these numbers we keep seeing in the media actually means. So in this case, we're going to use the rule of 72, which tells us that if something is doubling every n years, that means in 1 year it's increasing by 72 divided by n, right? Or in this case, about 3%. And what that tells us is that, yes, the electricity industry is big, it's basically, growing, but it's growing sort of in line with the rest of the economy. 3% is basically the average rate of growth in the entire economy, so the electricity industry is really not that special in that regard. All right, as for climate change, I think scientists make a very compelling case that, global warming is real, and that, the effect of, that the influence of man is having a real effect on the global climate. But it's the magnitudes and the consequences of these changes that are rarely talked about, right? And this is something that economists actually have spent a lot of time on. So if you take the sea level increase example, sea levels are rising, and scientists predict them to rise, but about as fast as they have been rising for the past 100 years. All right, and so yes, they're changing, but no faster than what we've basically dealt with in the past. Similarly, if you just more broadly, economists have tried to measure what's the net effect on of global GDP on the expected climate change, and the estimate is basically 1 to 2%, right? Maybe even zero. We'll get into the details of this in a future lecture, but the point is, it's not catastrophe, it's not calamity, it's 1 to 2%. So the point is not to say that these issues are unimportant and therefore you should not take this class. That's silly of me. The point is that there's more to these numbers than first meets the eye. All right. So yes, the industry is doubling, and every 25 years, and yes, that's in line with the rest of the economy. But the energy industry is a $1 trillion industry in the United States, right? It makes up about 10% of our GDP, and so just the fact that it's growing in line with the rest of the economy, it's still important. And for climate change, yeah, 0 to 3% may not be that big a deal, but 0 to 3% of the global economy equals trillions and trillions of dollars, right? So this is, so these are far-reaching consequences, and they still really matter. I just want to make sure that you're aware of the truth and don't just get sucked in by all the hype. So hopefully I've convinced you that this is an important issue. So the question remains, why listen to me about these issues? All right, so here, this is me. I am an economist, and first and foremost, the plan is to sort of tell you what the economic consensus is, right? I think economists are actually in surprising agreement on a lot of issues, and I'll try to focus on areas where we're in agreement for this course. I'll say a little more about this later. Furthermore, if you're curious, my background, I worked at Morgan Stanley as an analyst. I was the lead economist for energy and transportation at the White House Council of Economic Advisors. I've taught at Cornell University, and now I'm at Vassar College. I have degrees from MIT and Stanford in a range of different fields. More specifically, I said I'm an economist. I'm actually a behavioral economist, and my goal is to integrate a variety of disciplines into understanding a particular issue, and I'll try to sort of incorporate that interdisciplinary nature into this course as well. So what's going to be covered in this course? Basically, the course is going to cover the intersection of three things: economics, environment, and energy. Probably the largest part of this course is to use climate change, because climate change is an important issue for all three. The biggest source of the biggest contributing factor to climate change is in the fuels we burn to gather energy, and of course we're going to use the economic lens to understand all of these issues. Let me speak a little bit more about what economics has to say about the environment. And really, it actually has to say a lot. I remember one year when I taught this course, a student came to me before class and just looked at me funny, saying, "Really? What?" She couldn't comprehend what did economics and the environment have anything at all to do with each other. And the answer is really quite simple, right? Economics is really about the study of trade-offs, about how society deals with scarcity. And in the environment, even though it'd be nice to say we should do everything we can, there really are trade-offs. Right? Should we buy that hybrid car, even though we know that manufacturing that hybrid car is going to use dirty chemicals that might pollute the environment? Should we build those solar panels, even though building those solar panels might take up space that went to some endangered species habitat? Right? These are all trade-offs that are necessary for thinking about the environment, and economics actually has spent decades perfecting the tools for its study. More prosaically, there's lots of ways that economics comes into play. By executive order, economic cost-benefit analysis is the base of most federal regulation on the environment, and so understanding how economists think about this issue is important to think about federal regulation. And in some sense, it just makes sense, even if it feels icky to sort of put economic dollars and cents on environmental issues. And hopefully, in the upcoming lectures, I'll be able to convince you that this is the case. As for energy, I think it's less surprising that economists think a lot about energy and think about energy markets. One thing that may be more surprising is that energy markets are actually comparatively simple to a lot of the markets that we deal with, say like financial markets or housing markets. And so as a result, economics makes really sharp predictions about a lot of issues that you hear a lot of debate about. All right, so you hear a lot of debate about offshore drilling, dependence on foreign oil, electric cars, fuel economy standards, food for fuel, etc. All issues we'll be talking about in upcoming lectures that actually economists are all sort of agreed on, and they actually have a lot more certainty as to what the right approach is, which may not be obvious at all amidst all the political infighting and the political rhetoric. All right, so that brings me to my final point, which is basically my point of view for the remainder of this class. All right, which is I hope to convey to you the economic consensus as to how economists view issues of the environment and of energy. A lot of people out there are saying that we should pay more attention to scientists and the scientific consensus. But I think what's even more missing in the popular discourse is the economic consensus. And I think even the scientists themselves, who often advocate for one position or the other, often ignore the economic consequences of the positions they're taking. I know this is not the best time in the reputation of economists. I think a lot of people blamed us for not anticipating or preventing the financial crisis. I want to say that this class is more about microeconomics, not macroeconomics. And whereas on macroeconomic issues like finance and interest rates and unemployment, I think there's still a lot we don't know. On microeconomic issues, actually, I think economists are much more confident, right? So we have lots and lots of data from lots of industries to sort of back up the theories we've been developing for the past 100 years. And I think there's a large number of issues that economists are actually fairly confident about. And so what I want to emphasize is that the opinions presented here, they're not just opinions. They're not just from introspection. They're from decades of scientific inquiry based on theory, based on data, based on what the profession as a whole believes. And I hope, therefore, you'll find them worth listening to and take them seriously. But in any case, that's not for me to decide. That's for you. I'll be here no matter what. But I hope to see you as well. Anyways, thank you very much for listening. Until next time. Hello, welcome to the second lecture of the Economics of Energy and Environment series here at Udemy. This, as before, is Ben Ho, Assistant Professor of Economics at Vassar College. And my hope in today's lecture is to help all of you to start thinking like an economist by sort of conveying to you one of the fundamental principles of economics, cost-benefit analysis. I want to make sure that you're aware that despite all the inherent flaws and problems of this method, cost-benefit analysis is a very apt way to sort of organize our thinking about how to make decisions, both for policy and both for our day-to-day lives. Today we're going to talk about one of the central questions that have puzzled not just economists, but thinkers for centuries, if not millennia, and that's basically the question of how should society make decisions, or more fundamentally, what is the goal of society? The hope is to present to you that the economist view that decisions should be made based on cost-benefit analysis, and that the society should be trying to maximize benefits while minimizing costs may not be the ultimate answer to this question, but a reasonable answer to this question, because pretty much all of economic theory and everything I'm going to present for the rest of this course is going to be based on this idea. So, I'd like for you to consider this resolution, that basically the only policies society should implement are those whose benefits exceed the costs. I'm going to be arguing the economist side in this resolution, which is the affirmative that, cost-benefit analysis is the right way to sort of organize society. But I want you also to consider the negative side and all the flaws, because a lot of people, especially people that think about the environment, have a lot of problems with this resolution. I'm going to do my best to try to address these concerns, and I want to hope to convince you, maybe not that my answer is the right answer, but at least my answer is a reasonable answer, so that hopefully you'll be able to accept the premises that I'm going to present for the rest of this course. In some ways, this resolution is almost tautologically true, right? Just by definition of benefits and definition of costs. The benefits are the good things that come out of a policy, the costs are the bad things that come out of the policy, and if the good things outweigh the bad things, then we should implement that policy. More practically, this is also cost-benefit analysis is also the way that most governments evaluate policy. For the past 20 or 30 years, both Republican and Democrat presidencies have, by executive order, said that all federal regulations have to pass cost-benefit analysis in order to be enacted. And just specifically to sort of my field of economics, cost-benefit analysis, in some sense, the fundamental premise behind how economists sort of see the world. And so centuries of economics have sort of developed around this idea, and there's a lot of reason to believe that it works really well in understanding how society should operate. And so while I believe wholeheartedly that cost-benefit analysis is a sensible and reasonable and essentially right way to think about the world, if you do this thing just a little bit harder, you'll find that there are actually lots of flaws and lots of concerns with this simple approach. All right, so if I were sitting in a classroom right now doing this lecture, there's always a handful of lectures up in the air, dying to sort of point out why I'm wrong. And here I've collected some of the main reasons that people bring up. I'm sure there's more, and if there's more that you care about, feel free to add them to the discussion group below. I'll do my best to sort of address them. But here's some of the more popular ones. So one is, what about things we can't measure? Right, and the thing that comes up the most for things we can't measure is the value of human life. How do we trade off the value of, say, children dying of asthma due to pollution from the electricity plant with the value of sort of just cheaper electricity? All right, and actually, even though it sounds awful and it feels icky, economists actually have pretty good tools to determine just that. And so that we'll talk about that in the next lecture. Similarly, when it comes to, say, morality, there's this question of, what if the benefits are great and the costs are low, but it violates some fundamental, moral that people hold core. And as economists, I think we fully acknowledge that there may be moralities that are outside the scope. We just try to provide the objective scientific analysis, and then you could sort of apply your own morals to sort of to what you do with that. And then, sort of wrapped in with morality, though, is this question of whose costs and whose benefits. What if all the benefits accrue to basically a privileged elite and all the costs go to the relatively poor? Is that right? Is that fair? Economists actually has the right tools to deal with that, right? We think about that a lot, of dealing with inequality. And that, too, will be the subject of the next lecture as we sort of dig more deep into how cost-benefit analysis is actually done, especially in the context of the environment. To sort of prep you for this debate on, how do we value human life, and is it moral to do so, I'm going to encourage you to find this video on YouTube about Milton Friedman on self-interest. It should be relatively easy to find, and I'll try to include the links on the lecture homepage. So while I hope to have convinced you by the end of this lecture that cost-benefit analysis is the right way to go, there are a few alternatives that people use to evaluate policy, especially in the environmental sphere, so I just wanted to spend a minute or two to just sort of talk about them, and then argue that they're basically not inconsistent at all with cost-benefit analysis as properly applied. For example, the people that advocate sustainability say that we should be focused on choosing policies that will be able to sustain our way of life at its current level for now and into the future. Similarly, for those that advocate applying the precautionary principle, they say that society should take no actions that has any risk of endangering our current environmental systems. I think both offer a reasonable worldview on how to sort of think about policy, but I think cost-benefit analysis allows us to sort of share those same concerns, but do it in a more nuanced approach. I think the ideas of sustainability and precautionary principles say that we should avoid these bad things at all costs. And I think the cost-benefit analysis says that yes, basically losing the environment or endangering the current ecosystem is a cost, and we should definitely put that on the cost side, but we shouldn't avoid those costs, regardless of any benefits that may come about. Just as a pure hypothetical, suppose there's some kind of drug that could cure cancer for all humans, but in order to get this drug, we'd have to have a small 1% chance of destroying all the rainforests. The precautionary principle would say that we shouldn't do this because we have to preserve the rainforest. But cost-benefit analysis will say, well, maybe we should weigh, the cost of destroying the rainforest with the benefits of, say, curing cancer, and then sort of, figure out how to weigh the two combined. A third critique is basically sort of referred to as the biocentrism critique, which basically asks, why is it that we are focused on sort of humans in cost-benefit analysis when we should sort of think about focusing on animals and plants, right? So a lot of cost-benefit analysis sort of sees animals and plants as instrumental. We basically care about preserving animals and plants because they're useful for new drugs or for making us happier about our environment. But it's also reasonable to sort of argue that animals and plants have intrinsic value, right? That we should preserve a polar bear for the same reason we should preserve a person. I think that's perfectly okay, right? But I think that we could definitely easily incorporate that into cost-benefit analysis just by saying, okay, well, there is a benefit to saving a polar bear, just like there's a benefit in saving a human life. Finally, I mentioned earlier that there's a number of values that we may care about that are, difficult to quantify using cost-benefit analysis. The Nobel Prize-winning economist Amartya Sen sort of points to things like happiness, justice, dignity, or health as reasonable values. I think these are all fine. There are actually ways we can sort of, incorporate these things into our analysis. Or as I said before, the cost-benefit analysis is a starting point, and people should be free to sort of apply their own moral principles, as a way of thinking about how to interpret that and moving on. So I want to take this time now to turn to a brief review of supply and demand. Why? Well, partly because I'm an economist and we think about a lot of things in terms of supply and demand, but also more fundamentally, what you may not have appreciated when you learned economics way back when, is that supply and demand really is a picture of a cost-benefit analysis problem. So I'm going to be using these graphs a lot, and I'm not going to assume that you've seen it all before. I mean, they're not going to be integral to my argument, but for those who have seen a little bit of economics before, I think they often add a lot of insight into the ideas we're going to be talking about. All right, so to talk about supply and demand, we're going to have two axes. On the vertical axis is going to be price. On the horizontal axis is going to be quantity. And then, for supply and demand, there's going to be basically two curves. So I'm going to draw first. This is going to be the demand curve. It's worth pointing out that the demand curve is also essentially equal to the marginal benefit curve. All right. The curve is downward sloping because when the price is high, the quantity demanded is low. Right. Similarly, when the price is low, the quantity demanded is high. Right? Something that shouldn't at all be too surprising. We also call this the marginal benefit curve because, the price we're willing to pay is basically the benefit we're going to get from, buying this good, say, erasers, for example. So for the very first eraser I get, I'm willing to pay a whole lot, which basically means that this whole line represents the additional benefit I get from that one additional eraser. The second eraser, though, is just not as fun as that first eraser. So the second eraser I get, gives me this benefit. I'm willing to pay a little bit less. And for each additional eraser, I'm willing to pay a little bit less, a little bit less, a little bit less, until, I'm not willing to pay any more for erasers because I have plenty of erasers. Similarly, we could draw another curve. This is going to be the supply curve. And the supply curve is also known as the marginal cost curve. All right. So the supply curve is normally upward sloping because when the price is low, basically the companies were only going to supply, a very low number of erasers, for example. But when the price is high, companies are actually, happy to supply a lot of erasers because, well, if the price is good, let's sell as many as we can. And so we call the marginal cost curve the supply curve because basically the curve itself represents the cost the company has to pay to manufacture that eraser. All right, so let's say the first eraser is relatively easy to manufacture, so the costs are relatively low. But each additional eraser, let's say they start running out of rubber, they start running out of supplies, and so it gets more and more expensive. And so the area underneath the supply curve represents the cost the company has to pay in order to manufacture these erasers. All right, so if you recall, the demand curve represents the benefit consumers get from buying the erasers. The supply curve represents the costs the companies have to pay to manufacture the erasers. And so where they meet, is where the costs and benefits are exactly balanced, right here in the middle. All right, there's no reason why, basically manufacturers and consumers would choose to be at a lower level because at lower levels of erasers, the demand is really high, the costs are really low, the benefits outweigh the costs, so people are happy to manufacture more. And there's no point to be over here either because at very high level erasers, the costs are really high and the benefits are really low because the willingness to pay is really low. So also they wouldn't choose to be here. So in the end, markets sort of find an equilibrium where the cost of each additional eraser exactly is equal to the benefit of each additional eraser, and thus the market sort of performs this cost benefit analysis for us. So the point of all this is not to just impress you with my fancy math and graphing skills. The point of this is basically to illustrate probably one of the most beautiful results in all of economics, and that's the fundamental theorem of welfare economics. All right, and that basically says if we accept the premise that society is all about maximizing benefits and minimizing costs, economists sort of call this maximizing utility, then markets left to their own devices will do that job for us, right? The market forces of supply and demand will only cause people to take actions where the benefits maximize costs, and therefore the sort of overall welfare of society is maximized if left alone. All right, stated formally, the fundamental welfare theorem basically says that in complete and competitive markets of rational actors where supply meets demand, these markets are efficient, i.e. they maximize utility, by ensuring that the only actions people take are ones where benefits outweigh costs. All right. In essence, if markets are working, then society is best off. But I want to highlight three key words here because these three words are going to be the essence of environmental policy. All right. The three key words again were complete, competitive, and rational. And I highlight this because, this theorem doesn't say that we don't need government. The theorem says that, if markets are complete, competitive, and rational, then we don't need government. But oftentimes, in the case of the environment, or where there's often incomplete markets, or there's externalities, or there's monopolies, then the government is supposed to step in. What this theorem basically tells us, though, is that it gives us a guideline as to exactly when and how government should step in, and therefore is the basis of sort of formulating government policy, to fix the environment. So I apologize. The slide came out a little squiggly. I'll try to make sure that doesn't happen in future lectures. But so it's important to note that markets are not complete when there's externalities, right? And worrying about the environment is a classic externality. Markets are not competitive in the case of collusion or monopolies. And when we think about oil markets, there's there's potentially a lot of collusion and a lot of monopolies. And this logic may fail if people behave irrationally. And as a behavioral economist, I'll try to sort of highlight what we know about rational behavior and irrational behavior. I think rational behavior can explain a lot of what happens in the world, but it's important to be aware of irrational behavior as well. And so we'll come back to these, what are collectively called market failures, in a later lecture, because this again is going to be the backbone of how economists sort of think about environmental policy. All right, so let's just sort of wrap all this up. What I hope you get out of this lecture is that society should only undertake actions where the benefits outweigh the costs. At least that's the premise that economists sort of work on. We acknowledge that there's, entirely valid alternative point of views, but I hope you sort of consider this premise to be a reasonable one, because that's sort of the one, we as economists take. The second main point I want you to take from this lecture is that functioning markets, markets that are complete, competitive, and rational, are efficient because they ensure benefits minus costs are maximized. All right, and this is important because what this tells us is that if we want to fix the economy, if the government needs to sort of, maximize benefits and minimize costs, the way it should go about doing it is to make sure markets are functioning. And that often requires regulation, it often requires taxes, it often requires, government intervention. But, by understanding that markets, when they work well, this gives us direction as to how we should go about fixing things. And finally, as a preview for next time, I did mention some of those sort of the tricky issues of cost-benefit analysis, namely the difficulty of measuring costs and measuring benefits, and how do we think about benefits and costs that go to different people. We'll come back to all of these issues in the next lecture. Thanks for sticking around. Hope to see you next time.
Hi, and welcome to Lecture 3 of Udemy's course on Energy and Environmental Economics. As before, this is Ben Ho, Assistant Professor of Economics at Vassar College. In the last lecture, I tried to convince you that cost-benefit analysis is probably, a reasonable way to sort of evaluate, how you should take decisions, how society should make decisions. But especially in the context of the environment, there are a lot of sort of practical questions as to how we actually implement cost-benefit analysis that I hope to address today. I think one of the main reasons people object to using cost-benefit analysis to understanding environmental problems is precisely because the benefits are often so difficult to measure and so difficult to quantify. But yet, economists have spent decades trying to perfect their techniques, and I think we've come pretty close to coming up with convincing ways to sort of measure these environmental benefits. All right, we divide these benefits into two categories. The first is the tangible or use value of preserving the environment. These are the sort of the practical everyday uses of, say, discovering new medicines in the rainforest or preserving our parks to visit for recreation. The second is basically the intangible or non-use values of preserving the environment. These are just the idea of having a pristine Arctic National Wildlife Refuge, or preserving endangered species from being extinct. These are trickier to measure, but we have our techniques, and I'll discuss them, in the upcoming slides. Along the way, we have sort of three tricky questions that that come about when sort of measuring the benefits of the environment that I'll sort of talk about in length. One is how do we measure the value of life, the value of human life especially, but even the value of animal lives. The second is how do we measure the value of $1 to different people, right? So different people of different income levels or may experience the value of money differently. How can we accommodate that, especially when we're worried about inequality? And the third tricky question is how do we deal with uncertainty? Economists have a lot of tools of dealing with uncertainty, but especially when it comes to the tremendous amount of uncertainty with environmental outcomes, that's something that we'll definitely have to address when measuring environmental benefits. Take a second and ponder for a second how you would measure the use value of a few environmental goods people think about quite often. For example, what is the use value of a national park? Or how would you go about quantifying the use value of reducing factory emissions? What about the use value of cleaning up a toxic waste site? How about the use value of potential future medicine found in the Amazon rainforest? Or finally, what is the use value of having a night sky? All right, these are all sort of tricky questions, and economists actually develop tools to sort of address each of these. For example, the use value of a national park might be easiest, but I think economists tend to think that people are willing to pay what they value for something. All right, so if you value a candy bar at $2, then by paying $2 for the candy bar, you demonstrate that that's what you value the candy bar at. Similarly, for a national park, if we sort of had an entrance fee at the national park, and people are willing to pay that entrance fee, that gives us some measure of how much people are willing to pay to keep that national park alive, and the value that the national park creates for them. All right, that's the use value part. Another way that people sort of value national parks, especially ones that are free, is to see how much effort are people willing to put in to get to the national park, right? To say that if you're willing to put in, 5 hours of driving plus gasoline plus hotel stays just for the ability to visit the national park, we can sort of add up all those numbers and say, oh, well, maybe the value of the national park is, the value of the effort that you took to actually use it. What about the value of reducing factory emissions? So there's a couple of things here we could do. One is basically, so say the factory is polluting some, smelly gas that makes it unpleasant to live in. So what we could do is we can compare two houses, one by a clean factory and one by a dirty factory, and compare the difference in prices, right? So say the house by the clean factory is $20,000 and the one by the dirty factory is $10,000, then we could sort of infer from that the value of cleaning that factory up is going to be $10,000 of savings, and that's how much value we create by that's the benefit we create by cleaning that factory up. All right, we could do a similar approach to thinking about cleaning up a toxic waste site by comparing the change in local property values before that, with and without that waste site. We could also sort of add up the health consequences of having the toxic waste site there, or similarly the health consequences of having those factory emissions, right? And you could sort of add up. Okay, well, these emissions lead to an additional 3 cases of asthma each year in this town. We could go and sort of value how much do people spend to sort of avoid that asthma, or how much do people value their life with and without asthma, which we'll talk about a little bit when we talk about the value of life, and use that to sort of measure the use value of cleaning up emissions or cleaning up toxic waste. Down here, these are, here are 2 possible environmental benefits that, while are easy to quantify conceptually, are probably very difficult in practice, right? So people often talk about all the potential medical drugs that can be discovered in the Amazon rainforest. I think it's easy to quantify by just sort of saying, well, if you invent a new drug, you could sell that new drug for a certain amount of money, or that drug could basically, save a certain number of lives, and we'll quantify the number of lives coming up. But, how we could possibly predict how many drugs will exist in the rainforest, that's the far trickier question. And finally, you could think about even something as ephemeral as the night sky. We could think about how much are people willing to pay for a house where you could see the stars, where you could see the Milky Way. There's definitely something magical about seeing the Milky Way, as I remember sort of sitting in my car in Yellowstone National Park. And so the question is, if we could just see how much people are willing to pay for access to those, to see a beautiful sky, then that's another way economists use to quantify use values. Non-use values are we handle somewhat more straightforwardly, but sort of in a less satisfying way, right? Recall the non-use value is just basically the value of having that good or environmental benefit in existence just for the sake of being there. For example, what's the value of a pristine Arctic National Wildlife Refuge, right? If you don't recall, the Arctic National Wildlife Refuge is a refuge in Alaska, designed to sort of preserve the wildlife there that oil companies want to drill in. And so even though people may never visit, even though people may never sort of use that land, people like the idea of having it in a pristine condition. What about the value of a static climate? I'm not talking about all the use values of climate, of having a static climate, of sort of preserving our beaches, preserving our rainforests, preserving our climate, preserving our weather patterns as we know it. But what's this? Just the non-use value, right? Just the idea of sort of the pure idea of keeping the Earth as we found it. How do we sort of think about that? How do we quantify that? What about the existence of a national park you would never visit, right? So on the previous slide, we talked about how you quantify the value you enjoy from visiting a park, but there's definitely parks out there, like there's this, George Bush created this national park in the middle of the ocean around Hawaii that chances are no one's can get there, but it's a national park, and I think people are happy that it exists, but you'll never visit it, and so the question is, how do you quantify that happiness? And finally, perhaps, one of the most salient examples is, what's the value of preserving an animal from going extinct, right? There's tons of species of insects out there, insects, bears, birds, that might go away. We may never see these animals. We may never... we may never use them for pets or for food, but somehow it makes us feel bad that these things go away, and that and so preserving them actually has value that we should sort of quantify when we do cost-benefit analysis. So the standard way that economists use to sort of measure these things is something called contingent valuation, or in simple terms, just basically ask them. right? We just, there's a lot of, careful methodology for designing surveys, but we just ask, how much are you willing to pay to sort of keep the Arctic National Wildlife Refuge clean? How much would you be willing to pay to save panda bears? How much would you be willing to pay to save, I don't know, the spotted owl, right? And if we go to each person and we find that the average person is willing to pay, I don't know, $1 to save the spotted owl, and you basically add that up across all the people in the United States or all the people in the world, you get, if you focus on the United States, that's $300 million, and we say, okay, we should, as a society, the benefit to saving the spotted owl would be $300 million. However, Marty Weitzman, Harvard environmental economist, has pointed out that there's perils to this approach, right? And one of the perils to this approach is that it's often sort of quite arbitrary, right? So, so Weitzman went and looked at all the money that, the United States spends on preserving endangered species, and they find that, what predicts the species that as a country we support is not how ecologically valuable they are. It's not how inherently important they are. It's pretty much how cute they are and how big they are, right? His term for this is charismatic megafauna, right? That basically, the Americans like spending money to protect cute and cuddly big animals, right? So, I mean, it's probably no surprise that, in general, we much prefer protecting, the cute, cuddly panda bear rather than the smallpox virus. And maybe that's fine, right? Maybe the benefits should be based just purely on the animals that we find cute and cuddly. But, it sort of shows that there's something arbitrary about, about this approach of just sort of going by people's gut feelings as opposed to going based upon some rational reasoning. The other problem is that people often really don't have a good sense of how much they're willing to pay. Right? If I ask you, oh, would you be willing to protect the polar bear? You'll say, oh yeah, I'll pay $1 for that. And then I say, okay, what if I pick another animal? You say, okay, I'll pay $1 for that. And what about another animal? And you'll pay $1 for that. And pretty soon, if I just list enough animals, you might find yourself committing to say that I'm willing to pay. I'm sure I could list $1,000 or 1,000 animals or 10,000 animals on, that might be endangered, and you pretty much find yourself committing to paying $10,000 to protect endangered species, which on the whole is not realistic if you take a step back, right? But just when I present you one cute and cuddly animal at a time, quickly adds up to, quite a bit of money, and that people claim they value endangered species, but they may not actually place that same value on those endangered species. So just a quick summary of the different methodologies economists use to measure the benefits of environmental protection. Economists ideally prefer the revealed preference approach. The most direct application of this is basically just to look at market prices. How much you value for the candy bars, how much you're willing to pay for it. How much you value that national park is how much you're willing to pay to get in. All right, but when those are not available, then we could often apply to indirect costs. We look at sort of the travel costs of getting there. We look at hedonic values, which is like what I was saying about property prices. That basically people who buy property in neighborhoods by a polluting factory versus a non-polluting factory are we could compare the difference in prices to sort of get a sense of how much people value that pollution. Or how much money do people spend to avoid certain things, right? So if people spend a lot of money buying masks to avoid the pollution from nearby, then we could argue that the money people spend on masks is basically at least as high as the amount of pain or the amount of benefit they would get if we clean that pollution up. All right, so these are ideal because I think economists tend to believe people's actions much more than what they say. But if that's not available, then we turn to stated preference methods, which is just, again, like I said, asking them how much they care, how much they value the life of a polar bear. The direct approach of just asking directly is known as contingent valuation. There are also various indirect methods where we sort of give people, various choices that they have to decide and trade-offs they have to make that might, sort of get a more accurate approach, though still not as ideal as sort of our direct methods where we actually have an actual price for these things. And believe it or not, measuring those attributes of environmental protection, the value of a park, the value of a polar bear, that's actually some of the easier questions in environmental cost-benefit analysis. Here are a few of the trickier questions. All right, the tricky issue number one is, what is the value of a life? right? And let's just start with a question that sort of plagued philosophers for millennia. How much is a human life worth? All right, and the economist answer for that is actually quite simple. According to Economist, a human life is worth about $8 million. And I don't mean that to be flip, right? But that's just sort of what current economic studies say a human life is worth to Americans, anyways. People in other countries are probably worth different amounts, but this is the value the human government places on human life. You might wonder, how do economists calculate that? I think most people sort of assume that we calculate that based on your earnings potential, right? And I think that's the way that lawyers often use. Economists actually prefer a different one. All right, so if you think back when I said, what's the value of a human park? Well, the value of a human park is how much you're willing to pay for it. All right, so if you're willing to pay $20 for entrance fee to enter the park, then it stands to reason that you value that park at $20. Similarly, the value economists want to ascribe to human life is how much people are willing to pay to preserve their life. All right, and there's a whole number of ways of doing this, and the amazing thing is they all sort of give us the same answer. All right, so one way of doing this is pretty much to look at how much people are willing to pay for safety. So for a while back, before airbags were made mandatory, they were an option that you could buy, right? And so you could go to the car dealer, and there'd be some price, say $1,000 for airbags, and you would know that the airbags would reduce your chance of dying by some percent, and using that, doing some simple math, you could calculate how much people are willing to pay to save their life. All right. Similarly, you could think about jobs, right? So another place people looked for the value of human life is looking at different occupational choices. Many of you may not guess what's the most dangerous choice according to the census. The most dangerous occupation according to the census is maybe not what you'd expect. It's actually lumberjacks. All right, and I sometimes think that maybe we should have a holiday every year where we just sort of remember all the lumberjacks that have given their lives to bring us our paper. But it's definitely important, and people take the dangers of lumberjacking seriously. All right, and so and what studies have found by people like Kip Viscusi and others is that there are often different kinds of lumberjacking jobs, right? So say for example, there's one lumberjacking job that has a salary of say $30,000. All right. And say in this particular job, the chance of dying is 2 in 1,000. All right, and say there's another lumberjacking job, and the pay there is $22,000, and the chance of dying there is 1 in 1,000. All right, and so I'm not sure what the numbers actually were. These are just sort of hypothetical, but just based on these numbers alone, what you find is that lumberjacks, if these numbers are correct, are willing to sacrifice $8,000, right, 30,000 compared to 22,000, in order to reduce their chance of dying by 1 in 1,000. All right, and what that tells us is that the chance of reducing their chance of death by 1 in 1,000 times the value of their life is equal to $8,000, right? Or we could just sort of do some simple math, and that tells us that the value of a life to this lumberjack is equal to 8 million. All right, and it's just simple math just like this that economists have done across a whole wide variety of different contexts that tells us that people in general are willing to spend $8 million, to save their life. On average, statistically, right? It's not like people are, committing suicide for $8 million. It's that people are willing to reduce their chance of dying by say 1 in 1,000 for $8,000. And so as a policymaker, we should say, well, if people are willing to spend $8 million, that's exactly how much we should spend. Right? I mean, people often have this idea, and this was the Milton Friedman YouTube video I posted last time, that we should spend unlimited amounts of money for people's lives, right? We should spend 80 million, 800 million, that it's somehow inherently wrong to put any number on a human life.
but the thing is that, economics is all about dealing with scarcity. We don't have the resources to put unlimited amounts of money on people's lives. We need a number, and the most sensible number for us to use is the number people are willing to pay themselves to save their own lives. And so, as a result, the federal government basically pretty much uses $8 million. Most economists sort of use $8 million. And I hope to convince you that this is a reasonable way of sort of valuing people's lives, because this is often going to be an essential part of our calculations as to what we as policymakers should be doing. A similar issue that came up while I was working at the White House was, how do we apply this analysis to animals? All right, there was a regulation that sort of came through. So part of my job at the White House was to help evaluate all regulations the federal government was doing that was related to energy and environmental issues. And the regulation that came through was basically concerned about right whales. Right, the right whale is a kind of endangered whale that's found in the waters in North America, and the concern was that ships coming in would had some chance of hitting the right whale. And that and that every time the whale was hit by a ship, they might die. All right, not always, but sometimes. And this happens once or twice a year. And so the worry and so the response was that, in order to protect these whales from dying, we should put a speed limit. We should slow down every single ship coming into the United States, in order to protect these whales. All right, and in some sense that's fine, right? These whales have value, and we should worry about that. But there's a price to this, right? It's not free putting a speed limit. Slowing down all the ships means that goods and services that U.S. factories depend on, that U.S. jobs depend on, are going to get here slower. And if they get here slower, that basically means money. And and doing the math, basically on how much money is the U.S. economy losing to save each whale. The calculation for this regulation would basically put a price of several $100 million per whale saved. All right, and so it's interesting to compare that, implicitly, while regulations that the government passes to save human lives only spends $8 million to save a human life, inherently here this regulation is spending hundreds of millions of dollars to save whale lives. And you might, is this right? Is this wrong? It's hard to say. I mean, in some sense, it seems crazy to value a whale life above a human life. On the other hand, this whale is endangered, and so that every whale that dies brings us closer and closer to having this species of whale being gone forever. And so maybe we should be spending a lot more money to save these animals. But these are the issues that we sort of think about when we sort of tackle the costs and benefits of environmental protection. Another thorny issue when measuring the value of a life is how do we evaluate the life of a child versus the life of the elderly, right? So you might think, oh, every life is precious, and we basically should value them the same, and that's inherently what the federal government does, right? That if they're deciding between, say, building, I don't know, by locating a polluting source near a senior citizen home where two senior citizens' lives would be endangered, or by locating the pollution near a nursery where 2 baby lives would be endangered, the federal government by law has to sort of treat those lives exactly the same, and there's a nobility there. That sort of makes sense in a way that every human life is precious and every life should be treated equally. At the same time, you might also think that we should value them differently, right? That a baby has his whole life ahead of him, whereas a senior citizen may only have a few years left to live. So, so should we adjust for how many life years are left? Maybe yes, maybe no. And so, I mean, it's important to be aware of the implications of thinking about human life in this way. All right, I think it all sort of has a certain logical coherence, but we should be aware that it's not. It may have implications that we're not entirely comfortable with. One of Obama's and Clinton's economic advisors, Larry Summers, made this comment that says, "Oh, they're so poor in Sri Lanka, we should pretty much just ship all our nuclear waste there because they're happy to deal with it." Right? And in some sense, if we sort of think that Sri Lankans place a lower value on their life than Americans, that makes perfect economic sense. But it just sort of feels wrong, right? And he got in a lot of trouble for saying that. Similarly, if we think about all people value their lives the same, it makes sense though that
people with different income levels may choose to make different trade-offs, right, between spending money on protecting their own life versus spending money on other things they need, like food or shelter. All right, and so this was sort of evident in Katrina, where you find that the hurricane hurt mostly poor neighborhoods. Right, and this wasn't because God was punishing poor people, as some crazy pundit said. Right, this was basically because poor people choose to live in neighborhoods where that were inherently more dangerous. Right, and they chose to live in neighborhoods that are inherently more dangerous because the prices are cheaper. So they are compensated for the danger. Right, they had to pay less money for their housing because they lived in a dangerous part of town. And this monetary trade-off between danger and life is something that goes on every day, everywhere in the market. It feels wrong. All right, and so while I said I still think cost-benefit analysis is the right way to sort of think about these problems, it does force us to consider some serious ethical dilemmas of the choices we're inherently making every day in society. Another tricky issue of cost-benefit analysis is when we talk about the benefit of $1, $1 here, $1 there. We haven't made a distinction as to a dollar to who. All right, and the relatively easier question to address is how do we value the dollar to, say, an American versus the value of a dollar to, say, a Bangladeshi? That's something that economists deal with pretty well. Right, so people often worry that cost-benefit analysis doesn't take inequality into account. Well, actually, I think it usually does. Right, when economists sort of do this, we recognize that $1 is worth a lot more to a poor person than a rich person. That if Bill Gates was walking down the street and stumbled across $1 million, that'd be worth very little to him. He wouldn't even have noticed because he makes $1 million, breathing every 5 minutes. But for most of us, if we bump into $1 million, it's worth a lot more. And so we basically sort of have a multiplier factor, right? Where we basically sort of talk about, we sort of estimate how much is a dollar worth to an American versus how much is a dollar worth to a Bangladeshi or Indian or South African or French or German or whatnot. And and we sort of and when we sort of evaluate the cost benefits, we sort of take into account how wealthy is that person in that country, so to make sure that the benefits that go to a Bangladeshi are worth a lot more than the benefits that go to Americans, right? And that sort of advocates, that might advocate having us trade off, putting out some costs on Americans in favor of benefiting poorer countries. All right, and so economists in this sense are not as heartless as people sort of think we are. The trickier question, the one that economists actually really have no clue of yet as to how to resolve, is what's called sort of the delta debate, or how do we value the value of $1 to people today versus the value of $1 to people living 100 years from now. All right, and so in some sense, this part of this debate was started recently by the Stern report. Nicholas Stern is a British economist who basically said that out of ethical fairness, we should value all people the same. It doesn't matter if they're living today. It doesn't matter if they're living in the future. It doesn't matter if they're living 200 years from now. All right, and well, ethically that sort of feels right. If you sort of think through the implications of what that means, it doesn't make sense at all. All right, so William Nordhaus, another famous environmental economist you'll hear about a lot throughout this course, pointed out that if you really believed, in Nicholas Stern's numbers, that means if the lives of the people in the future mean so much, we should be willing to sort of sacrifice everything today so our children are better off. Right, that it's in some sense selfish for us to be spending any money at all on ourselves. Because if we just sort of sacrifice everything we have and just give it and leave it to our children, our children are going to enjoy the fruits of those benefits for hundreds, thousands, millions of years. Whereas and so if we value their lives equally, then that's what we should be willing to do. And somehow that sort of feels wrong. Right? And the other reason why this sort of feels wrong is that our children are going to be richer than we are. Right? I mean, despite the fact that growth is slowing down, it's still doubling every, say, 20 or 30 years, which basically means if we go to 100 years from now, our great-grandchildren are going to be roughly 10 times richer than we are today. Right? So why should we be sacrificing money today in order to make our great-grandkids feel better, better off, because they're going to be so much richer than we are. They'll be richer, they'll be more equipped to deal with the problems. Why don't we have them sort of, have them sort of subsidize us because they're relatively better off because we've created the economy to provide for them. And so the number that economists use to sort of measure this, to measure how much we should trade off, values today versus values of the future, is known as delta. And this is sort of a thorny issue that economists still haven't fully resolved how to deal with. The final tricky issue is understanding what is the value of a gamble, right? How do we deal with risk? So economists actually have a long developed tradition, going back 100 years, of sort of thinking about risk. We sort of take the probabilistic view on the whole and think about expected values and expected utility. It's important to point out that these two things are not necessarily the same, right? That say imagine you earn $50,000 a year, and you want to compare either a 50% chance of losing $1,000 or a 1% chance of losing $50,000. All right, and you want to say which one would you prefer? And of course, I think most people would sort of prefer the first, right? So the expected value of these two things are both the same, right? The expected value of both is equal to $500, right? But the expected utility is quite different, right? Because losing $1,000 is painful, but losing $50,000 or all your income for the year is very, very painful. And so this is especially relevant when thinking about environmental issues, because oftentimes what we're talking about is not it's not small losses. It's not like a 1 or 2% loss. What we're really worried about is the tiny percent chance of losing everything, right? The tiny percent chance that that we have sort of major changes that sort of make human living unbearable somehow. All right, and the harder problem there is that we don't even know what these percentages are, right? We don't know if it's 1% or 0.1% or 2% or 3%. The scientists have a pretty good answer as to what the average effect is of climate change. I think our knowledge there is pretty clear, but it's the percent probability of a catastrophic change that we haven't been able to pin down, right? Where 1% probability versus a 2% probability, while only a 1% difference has huge effects as to how we should how we should respond and how should we behave. A related issue when sort of thinking about how we should deal with gambles is what's sort of known as real option analysis. All right, so a lot of you have heard of stock options as something that companies give, but probably a lot of people haven't really thought about exactly what a stock option actually is. And what a stock option actually is basically it's the value of waiting and seeing is what I call it, right? It's basically the idea that, well, I don't, is the idea. Yes, I could choose either to buy the stock today, or it's even better is I could choose to wait and see and decide to buy the stock later, right? A stock option is the option to buy sometime between now and the future. And and what's nice about option analysis is that we actually have really good financial models, right? Sort of Black-Scholes models and things that tells us that allows us to quantify pretty precisely what the value is of waiting and seeing. This is going to be important when we think about environmental policy because there's a lot we don't know yet about about what we should do with the environment. I think economists are almost all agree that we should do something. What we don't agree on necessarily is when we should do it. All right, because we could either do it now, where it's going to be expensive and there's a lot of uncertainty, or we could wait and see, right, and do it in the future, where our kids are going to be richer, they'll be better equipped to handle it, they'll have better technology, they'll have less uncertainty. All right, and sort of how you weigh doing it now versus doing it in the future is going to depend a lot on sort of the value of the option. All right, so I've talked a lot about sort of thinking about the benefits of environmental protection. The flip side of the coin is how do we think about the costs of environmental protection? All right, and here economists, don't have as much to say. One way economists are thinking about the cost is basically, well, we just do surveys, right? Just like for the benefits, we ask them. For the cost side, we also sort of ask them. And we say, okay, well, how much will it cost you to sort of build, to build something to reduce emissions? Or how much will it cost you to build, not in the endangered wetland, but in some other piece of land, right? And so this is one way to do it. Another way is just the engineering approach, where you basically go to engineers and say, okay, well, what are the various technologies you would need to sort of achieve this environmental protection? What would you have to build to sort of reduce the emissions? What would you have to build to sort of protect this polar bear habitat? Ask the engineers to sort of come up with their best estimates for how much it would cost and go about it that way. And then the third way is basically just to look at supply and demand estimates, right? Just look at the market. Look at how much compare how much it costs to sort of buy electricity that's clean versus buy electricity that's dirty, and sort of use that to sort of get an estimate of how much it costs to produce clean electricity. And I think this is the ideal approach, because surveys and sort of engineering estimates are always fraught with error. People often will overstate or understate based on their own prejudices. But the market really basically says that, well, people are putting their own money on the line. And so just like on the benefit side, where we prefer to sort of see how much people are willing to pay, actually for these environmental benefits, it's also useful on the cost side to see how much are people willing to pay actually for these environmental protection technologies. All right, just to sort of wrap things up here. So in these first couple lectures, I've basically tried to sort of give you a sense of cost-benefit analysis and tried to convince you that it's a good approach to seeing the world. In the lecture today, I've sort of gone over some of the sort of technical and thorny issues of actually applying cost-benefit analysis to thinking about environmental problems. Next week, we're going to turn back to sort of thinking about the energy side of things, but also just economics generally, and talk about supply and demand. Right, and supply and demand is probably sort of the heart of economics, at least at the undergraduate level. It's going to be a powerful tool for us when thinking about a lot of energy issues and environmental issues. So I hope to see you all then. Thank you very much.
Hello and welcome to the lecture on supply and demand as part of the Udemy series on energy and environmental economics. As always, this is Ben Ho, Assistant Professor of Economics at Vassar College. I'm here to walk you through this. Supply and demand is one of the central concepts in economics, and so I think it serves as a good foundation for a lot of the policy analysis that we'll be working on later on. One thing I want to warn you, though, is that this lecture will be sort of more on the technical side. So for those of you that sort of want to avoid graphs and sort of think more about sort of the practical discussions when it comes to environmental economics, you may want to come back in 2 lectures when we start talking about climate change and how all those practical details matter. But for those of you who are sticking with me, the plan for today is we'll be talking about how supply and demand works and how it applies to the fundamental welfare theorem, which will give you some idea of why economists sort of think this idea is so important. Then we'll sort of focus on a couple applications. This question of, is the world running out of oil? And this question of, should the United States drill in the Arctic National Wildlife Refuge in Alaska? These last 2 applications I'll sort of introduce right now, which is the effect of supply and demand and thinking about OPEC and thinking about externalities. We'll cover these in more detail in upcoming lectures, but I'll just sort of highlight why they're important. And for those of you that want to learn more, there's tons and tons of resources online to talk about supply and demand. So here we'll focus primarily on how supply and demand can be used to sort of answer puzzles related to economics of energy and the economics of the environment. So just a quick recap on supply and demand for those of you that missed the earlier lecture. The supply and demand basically is the tool that economists use to determine the price and quantity of goods in a market. All right. So if we want to say, how many CDs should be out there, how many CDs do we expect in a market, and what price will they sell at, and how many will be sold, we turn to the supply and demand graph. All right. And typically the supply graph looks something like this. Looks something like this. Right? This is the supply graph. The supply graph, represents the marginal cost of production. So, I often sort of think about this as the marginal cost graph. And it basically looks like the way it does because it's telling us how costly is it for firms to produce a certain quantity of good. All right. So if the supply curve looks like this, the marginal cost of the first good down here is quite low. Right, but as the quantity moves up, the cost gets higher and higher. Right, and this represents the supply of a craft that basically of a firm or industry where costs get higher and higher the more and more you produce. There may be other supply curves that are sort of flat or downward sloping for, say, manufactured goods, for intellectual property, and those are going to be relevant for other markets, but for like natural resource markets, like what we'll be dealing with the most often when it comes to energy and environmental issues, this is fully appropriate. Now the demand curve is going to be downward sloping.
All right, and just like the supply curve sort of represents the marginal cost for the firms, the demand curve represents the marginal benefit for consumers. All right, and it's sort of shaped the way it does because for the very first unit of that people may purchase, imagine that this is the only CD in the world, the only in environmental goods we might think about the only barrel of oil. If we only produce one, that first barrel of oil is going to be really, really expensive. But as we produce, as more and more oil is sold on the market, basically the people buying it, they benefit less and less, right? So the people up here who are buying it, they value the oil a lot. The people down here buying it, if the oil is cheap, they'll buy it. And somewhere where supply meets demand is exactly where the benefits of producing that additional barrel of oil is exactly equal to the costs, right? So for example, if we produce less oil than this equilibrium quantity, right? So what we could draw this equilibrium quantity as, this line here, where, we sort of draw Q star. Then basically for all points, didn't want to do that. So for all points to the left of this equilibrium quantity, right, the benefits are going to exceed the costs, which basically means that there's more buyers out there than sellers, which basically means that that basically the firms are going to have incentive to produce more and more goods up until you get to the point of Q star. And if, for example, if there's didn't want to do that. Let's see. If, on the other hand, there is sort of you're over here to the right of the Q star, where there's sort of more sellers than buyers, well, there's basically going to be too many goods out there, and so people are going to start discounting what's available, and cutting back on their production, so that you sort of return to this equilibrium where supply is exactly equal to demand. And while these may seem to be like sort of some dry concepts, right, of just like graphs and lines and prices and quantities, it actually has some really important applications, right? One of the first applications is, what I call helps solve the IKEA puzzle. All right, and this is this puzzle that a friend of mine, she's a physicist, and she we're talking about buying furniture, right? And for those of you that haven't been to the apartment of a 20 to 30-year-old these days, you'll find that pretty much all the furniture is IKEA, just because it's so much cheaper than everywhere else. But for 20-something-year-olds, basically people puzzle over this question, right? Which is, is it socially conscious to buy furniture from IKEA? All right, and so why is this? So my smart physicist friend, she basically said, well, why should there's all these sort of costs associated with buying IKEA, and costs and benefits that just seem intangible, right? So buying IKEA basically means cutting down more trees. IKEA has this reputation for being disposable, so it means buying new furniture every few years, even though it's cheaper. It basically means more garbage in landfills. It basically means more deforestation. It basically means more manufacturing. It means shipping the furniture over from overseas. Here's a list of some of the concerns she came up with. All right, and so one thing I want to emphasize is that what's powerful about thinking about markets through supply and demand is that if markets are working, right? If you recall that when we talk about the fundamental welfare theorem, it says that if markets are working, which means that they're complete, which means that they are efficient, which means that people are rational, then actually all these costs and benefits are automatically accounted for. All right, because basically somewhere along the lines, for a firm to basically produce a certain good, that basically he had to pay the cost, and so all the costs associated with that good is wrapped up in the supply curve. All right, and then all the benefits, or all the costs and benefits that the consumers have to face, in terms of dealing with throwing things away, in terms of sort of dealing with buying furniture over and over again. All these things are associated with the benefit the consumer receives from buying the good, right? And that means that at the point of market equilibrium, where demand is equal to supply, we know that if the consumer is willing to buy the good, then the benefits must outweigh the costs. That means that the value to society of buying IKEA must be greater than the cost to society, if the markets are complete. All right, and so you might think that, oh, so in terms of like deforestation, yes, we're cutting trees down and that's costly, but IKEA had to buy the trees from somewhere, and so those costs are accounted for when IKEA bought the trees. In terms of the cost of landfilling furniture, someone has to pay to put the trash in the landfill, and if the consumer has to pay to put the trash in landfills, then that works into the demand curve. And so long as all these costs and benefits are accounted for in markets, this super complicated problem all of a sudden becomes easy. The market takes care of it, right? The question just becomes, am I willing to pay the price? If I am, that must mean that the benefit of doing this outweighs the cost of society, and we don't have to fret. Of course, all this relies on the rather strong assumption that all the costs are accounted for and people have to pay for the costs, right? So I think a common one when we think about environmental goods is, what about the cost of emissions, right? What about the cost of spewing all that carbon dioxide as you're manufacturing the good? What about the cost of spewing all those sulfur dioxide to produce the goods? I mean, the thing is, actually, in most countries, even the U.S., most emissions are regulated, right? So in the United States, if you're emitting sulfur dioxide in the air, you're gonna have to pay for a permit, and so actually those costs are already accounted for. Carbon dioxide is not regulated in the United States, and that is a problem, but it is regulated in Europe. And so long as you believe that it's properly regulated in Europe, then those costs are also accounted for. There's a big debate as to what the cost of those permits should be, and we'll come back to those when we come back to the practicalities of implementing these issues. But if you assume that the regulations were written correctly, then again, markets work. All right, and then the other thorny issue is how do markets get regulated? How should we price? How should we make sure companies pay the full price of things like emissions and deforestation, for example? And that we'll sort of address in future lectures as well. So here, let's turn to the first application, right? Which is this question of, is the world running out of oil? All right. Oops, I keep doing that. Basically, this comes up all the time, right? At least up until a couple years ago. So now people, with gasoline prices sort of falling slightly, people don't talk about it as much. But I used to get periodic emails from my high school friend who was sort of paranoid about the world coming out of oil. He had this image of sort of Mad Max and Thunderdome and the world coming to an end, and chaos breaking out in the streets. I just read this great book, Ready Player One, and the whole premise of that is that the world runs out of oil, and civilization comes to an end. All right, and I think this is the kind of question where if you talk to pretty much any economist, it's they sort of think that it's crazy, right? So I want to sort of have this very simple proof and for the proposition that the world will never run out of oil. All right, and how am I going to prove that? Very simply, my proof is simply this. Done. All right, so ponder that for a second. What have I done here? This is a supply line. All right, what this basically means is that oil, like pretty much most natural resources, has an increasing supply curve. Right, which basically means that the first drops of oil were relatively cheap and relatively easy to access. But as we get higher, and let's say the price of oil, it varies a lot. For simplicity, we'll just say the price of oil today is $100, right? And so that means that at $100, all the oil that's available for less than $100, all the oil that's over here, basically all this oil is going to be produced. All right, but that means there's all this oil up here at a price above $100 that's not going to be produced. All right, and so that's not currently being produced. And so even as sort of oil runs out of the ground, that basically means there's all this oil at higher and higher prices where that's always going to be left. And so you might say, okay, as the easily tapped reserves start running out, we're going to have to sort of tap more and more reserves. Yeah, that's true. Actually, empirically, that hasn't happened, right? I think a sort of interesting side note on this discussion is that if you go back 100 years and sort of plot how much oil scientists think is in the ground, it looks sort of something like this, right? So this is like 1900, and this is today. If you sort of like plot like the official estimates for how much oil is left in the ground, it looks like this. Right, so quite the opposite of the world running out of oil as we sort of pull it out of the ground. It's like every year there's new discoveries. We find more and more oil that we hadn't had access to before. oil out of rocks, oil deep in the ocean, oil under the Arctic poles. And of course, this can't go on forever. Of course, at some point we'll realize that we'll find all the oil there is to be found. But the thing is, long before we get to that day, all right, we're going to get to the point where the price of oil is basically just too high that we're going to switch to alternatives. All right, so yeah, maybe the price of oil will go up to $100, $150, $200, but at some point there's going to be oil that costs more than that. That's going to be in the ground that we're just never going to exploit because there's no need, right? Because once oil hits $200, a wealth of alternatives, are easily can come online. Right, so there's the official estimates. Back when I was working at the White House, you could go back and look at the economic report of the president from 2006, where we did estimates on what's available at different price points, and you find that once oil hits $200, we could, instead of using oil, we could switch to electric cars and run our cars from solar panels, or we could switch to ethanol-based cars and run our cars based on corn or bamboo or or grass. All right, so. The main point is that, yes, oil might get more and more expensive as as the easy deposits of oil start running out. These will start running out, and we'll have to turn the deposits up here. But the idea that oil can run out is frankly just economically impossible. Another nice application of supply and demand is that it could basically help answer some of the questions about drilling for oil. All right, about a few years ago, people haven't talked about it as much, is this question of whether the U.S. should be drilling in the Arctic National Wildlife Refuge in Alaska. All right, for those of you that don't know, this is a piece of land in Alaska set aside to preserve a national habitat for a lot of wild animals. We know that there's a large deposit of oil there, and oil companies claim that they could basically drill there without disturbing the natural habitat. But of course, environmentalists are skeptical, and so as a result, the federal government has not allowed oil companies to sort of take advantage of this oil resource. All right, if you recall, this was part of the debate in 2008 in the presidential election with Sarah Palin's famous line, "Drill, baby, drill." All right, and under the Obama administration, actually Obama has opened up a lot of oil drilling in sort of the outer continental shelf, sort of in the oceans off the shore of the United States. Drilling in the Arctic National Wildlife Refuge, or ANWR as the acronym goes, has still been prohibited. All right, and so let's think about the economics of this and think about, who's right. Was it, Sarah Palin and the Republicans right about this, that we should be drilling, or is it maybe the environmental activists that are right, that we should not be drilling, and what are the consequences? Well, here's some facts to sort of frame it. All right, so the estimates vary widely as to, how much oil is actually there. But I think, one sort of estimate that I sort of saw, that I sort of believe in, is you could roughly say there's 800,000 barrels of oil each day possible from ANWR, or maybe 10 billion barrels of oil total over the life of the well. All right, and actually in the world, to make the math easier, let's say the world currently produces about 80 million barrels of oil each day. All right, and so if you just sort of take that math and say 800,000. Right, divided by 80 million, you would see that, the effect of drilling at ANWR is about a 1% increase in the supply of oil. All right, and so is 1% a lot? Is 1% a little? It's hard to say, right? But supply and demand can actually tell us exactly, what the effect of 1% is going to be. All right, and how does it do that? So if we just sort of see that, what happens is that, let's say we draw, let's see, don't want to do that. Let's say we draw a demand curve and a supply curve, right? So this is going to be our demand curve for oil, and our supply curve will look like this, pre-ANWR. Right? What happens is, what happens if we start drilling in ANWR is that we'll get 1% more supply. All right. So supply, instead of looking like this, will basically look like this. And what's the effect? And so that basically means that there's going to be this shift. All right, and so this distance is going to increase by 1%. All right, and how is that going to change? Well, that's going to change because basically the old price and quantity are going to be here, and the new price and quantity are going to be down here, and so we'll basically get more oil, not 1% more oil, but somewhat more oil used in the world, and the price of oil will come down. All right. So, in some sense, the Republicans are right. Drilling for oil is a good thing. But let's look at this a little more carefully. All right, so zooming in on this sort of portion of the graph just a little bit. All right, so what basically what we find is that, okay, if there's a supply increase of oil that moves us from here to here by 1%, then the price of oil is going to drop from here to here. All right, and how much that price is going to drop is going to depend on the slope. All right, the slope of the demand curve, here, the slope of the demand curve here, and also the slope of the supply curves here. All right, and so basically, going back to some high school algebra, we could once we know the slope of these curves, we could basically calculate how big the price change is for a 1% increase in supply. All right, and so you could go online and just sort of Google the words elasticity of oil supply, elasticity of oil demand. All right, because economists have gone and sort of calculated the slopes of various kinds of commodities, and what you'll find is that those numbers are readily available. All right, so the numbers for the elasticity of oil supply is about, say, 0.4, and the elasticity of oil demand is about negative 0.4. Roughly, I mean, so these slopes sort of change depending on, geopolitical considerations, technology, etc. But as a long run average, that's basically about right. All right, and so once we have these elasticities in hand, we could basically, it's fairly easy to use some math to sort of derive. Oops, didn't want to do that. To basically derive, all right, I just wanted to move the arrow. All right, let's make a new arrow. To basically derive this equation here. All right. So this equation basically tells us that if we know the elasticity of supply, and if we know the elasticity of demand, and if we know the percent change in the quantity, which is 1% right here, then we can calculate the percent change in price. All right, and so just doing some simple math with that, you could find that the percent change in price is just equal to 1% divided by 0.8, which basically equals 1.25% is this change in price right here. All right, so yes, all right, so we know that, so that's basically we expect a decrease in price of 1.25%. All right, and so yes, we know that drilling in Anwar, it's good. We'll have higher supply, and yes, it will bring the price of oil down. All right, but the math of supply and demand tells us that the net effect of drilling is actually really tiny, right? Okay, so if the price of gasoline is $4, this says the price of gasoline should fall by 1.25%, or $3.96 about. All right, so it's important to sort of be aware, to be wary of sort of these arguments that we should be drilling for oil because it'll bring the price of oil down. It frankly won't. Right? The price of oil is a world market. Even though there's lots and lots of oil in Anwar, the net effect is pretty tiny. So, should we now conclude then that the Republicans are crazy and there's absolutely no reason to drill for oil in Anwar? Not at all, right? So if you go back and the number we had before was that there's roughly 10 billion barrels of oil sort of sitting there. I mean, they're more or less depending on the estimate. You don't know for sure, but 10 billion is a nice easy round number. Right? So if you think about what's 10 billion barrels of oil actually mean, well, 10 billion barrels of oil sold at $100 a barrel, that's basically $1 trillion of oil. All right? So you have all these people sort of fretting over the debt, over the national debt, and of course it won't pay off the national debt, but it'll pay off a good chunk of the national debt. Right? 1 trillion is a lot of money. Another way to think about this is that 1 trillion divided by, sort of if we distributed that in checks to over the 100 million households in the United States, that's $10,000 per household, right? So we're talking about, $10,000 per household of $10,000 of oil per household that we're just leaving in the ground, ignoring, because we're worried about, some polar bears. Maybe that's worth it, maybe not, but it makes the question a lot harder, right? So it's not that the price of oil is going to go down. That's not a reason why we should drill, but $1 trillion is real money. All right. Another way to sort of think about this is is that, well, that's fine, it's $1 trillion, but the oil companies are going to take all that money. Well, they're going to take, well, part of it is that, well, the oil companies are owned by people, and so the owners of the oil companies, the shareholders, and anyone that owns a pension fund, anyone that has a retirement like savings account, is going to get some of that money that way. On top of that, the government is going to charge high royalties, high taxes, and it's not crazy to think that the government is going to, sort of take half those proceeds and, and again, use that money to pay down the debt, or, give everyone $5,000 tax credit, right? Something. And so, these are the numbers that are worth keeping in mind as we sort of think about whether to drill or not. I'm not saying we should. There are real environmental consequences to think about, and how we value those. Well, we talked about those in an earlier lecture, but these are the decisions that have to be made. All right, 2 final applications that I'll hold off to a future lecture, but I think are worth talking about. One is, what's the effect of OPEC? Right, this is the group of the Organization of Petroleum Exporting Countries, primarily led by Saudi Arabia, but includes countries around the world that try to keep the price of oil high. All right, and the other application of supply and demand is we could think about how do externalities fit in, right? So as I talked about earlier in the IKEA example, supply and demand only works out for the best of society if all the markets are complete. But if markets are incomplete and there's things that the markets aren't accounting for, like pollution, like endangered species, like cute and cuddly animals, then markets fail. All right. One interesting thing about these two applications is that they actually sort of almost cancel each other out a little bit, right? So if you believe that OPEC is powerful and they're making oil prices too high, well, that's good, because externalities say that actually oil prices are too low, right? Externalities say that the price of oil should be higher because we're not accounting for all these external costs, and so we need to raise the price. And in some sense, one thing you don't think about very often is that OPEC is actually raising those costs for us. Anyways, these are interesting implications, and we'll come back to both of those externalities in the next lecture, and OPEC in a lecture down the line. All right, just to summarize, supply and demand is a pretty good way to model markets. It could sort of answer a lot of the questions posed in today's policy debates that I think, people don't think about things this way, right? You hear a lot of debate about the world running out of oil. You hear a lot of debate about whether to drill, and I think the simple economics actually goes a long way in sort of illuminating the net effects of those policies. For next time, we're going to basically dig into externalities some more. What happens when markets are incomplete? We'll think about how to model them, what counts as externality, what doesn't count as an externality, how should they be measured, and because I think this is the central question when thinking about how to protect the environment. Thanks for joining me. I'll see you all next time. Welcome to the Externalities lecture on the Udemy course for Energy and Environmental Economics. As always, this is Ben Ho, Assistant Professor of Economics at Vassar College, here to explain to you how economics can explain energy and environmental policy. This is, as I mentioned last time, this is the last of the introductory course lectures here that are sort of more on the theoretical and abstract side. For the rest of this course series, I'll be dealing with more practical matters such as climate change and agriculture and biofuels and that sort of thing. So for those of you that have been eagerly anticipating some more applied policy issues, I assure you, it's coming soon. But hopefully, but when we get there, you'll have a pretty solid groundwork of how all this fits together. So recall that the fundamental welfare theorem that we discussed in earlier lectures basically said that if markets are sort of complete, competitive, and composed of rational actors, then supply and demand are going to ensure that the efficient allocation is achieved. All right? Because basically, in such a market, every actor is only going to make a choice where the benefits outweigh the costs. Therefore, cost versus benefits are maximized, and therefore, society is as good off as possible. All right. Today we're going to talk about one of the reasons this can break down, and this is for the complete assumption, and we're going to talk about what happens when markets are incomplete. All right. Oops. The formal definition of what we get when we have an incomplete market is an externality. Sorry about the jiggling. Is an externality And an externality is one of the primary justifications for government action. For example, one of the primary externalities that we care about for this lecture, environmental externalities, basically accounts for, say, 1 to 2% of GDP spending in terms of government regulations and government programs. All right, so 1 to 2%, that's basically, tens of billions of dollars and quite a significant part of the U.S. economy. I think anyone who's ever taken an economics class probably has some idea of what an externality is all about. But I think it's important to be sort of precise with the definition. All right, so an externality, as economists define it, is basically an outcome of an economic activity where property rights over the outcome are unenforced or undefined. All right, in some sense, it's basically an outcome of an economic transaction that's external to the participants in the market. All right, and the reason this is important is because when property rights are, unenforced or undefined, the markets do not exist. They are incomplete. Thus, the fundamental welfare theorem does not hold. Therefore, government intervention in these cases is justified. I think, though, of course, to expand on the definition, to say that if we say externalities are what happens when property is undefined, we have to take a step back and say, well, what is property? Right? I think property is one of those sort of words that we sort of take for granted. We sort of seem to know what it means, but it's often hard to sort of precisely pin down. So in our context here, property is the set of rights of control, right? The right to benefit from something, the right to sell, right to benefit, the right to sell, or the right to exclude. All right, it's important to know that property is a bundle of rights, right? So that if I own a piece of land, I may have the right to farm on it, but I may not have the right to build a skyscraper on it. All right, so property is not just like the physical object, but it's the right to all the individual uses of that object. And all those uses, you could benefit from those uses, you could sell those uses, and you could exclude other people from that usage. A sort of minor side point to this is, what does it mean to own something? Well, oftentimes, I think the way economists think about ownership is that the owner is the residual claimant, which means that the owner is the person that has all the rights that are not claimed by anybody else. All right. I mean, for our purposes here in economics, I think we're going to say that the property is the rights necessary to engage in market transactions, where a market transaction is defined as a mutually agreed upon transfer of properties. Now, all of this is sort of rather abstract, and so to make things more concrete, the best way to sort of see this is through some examples. All right. So take for a second, maybe pause the video and think about what are some examples of externalities? Jot some down. All right. I think it's going to be very important to be very careful how we define externalities, because a lot of things that people think are externalities aren't in fact externalities. So when I do this in class, I often sort of ask people to think of some externalities, and these are things that people come up with, and it's generally not very hard, right? So a classic. So on this side here, I'm basically going to draw, these are all negative externalities, all right? So a classic example of a negative externality is noise pollution, right? Where basically, I'm at home, I'm consuming my own music, I bought the music, I paid the music provider for the music, I listen to the music, I'm consuming the music, and that's all great, but, the music is loud, and if it bothers my neighbors, that's an externality, right? Because my neighbors were not involved in that transaction. They didn't participate in this. They in some sense they could be involved in a transaction if they had ownership over the noise rights in my building, but because in general those the rights to sort of regulate the noise in the building are not normally enforced, that's considered an externality. The classic externalities we think about when we think about sort of the environment is basically things like pollution, right? Air pollution, with factories producing gases, water pollution with companies dumping. Crime in some sense creates an externality because because of the fear involved and the money people spend trying to prevent crime. But it's important to be very careful because these parts of these things, air pollution and water pollution, are externalities, but other parts are not. All right. For example, easier example to think about is that water pollution, where the company is dumping into its own lake, and that's not an externality. All right, because it's hurting the lake. But if it owns the lake, then it basically is bearing the full costs. And then you might think, oh, but what if the company is not, what if the company is not, is using the lake for its own evil purposes, and the lake would be better used by as for recreation, for for nature. Well, the answer to that is that if it would be better used for recreation or just to enjoy the natural wilderness, then the people that would have enjoyed it more should have bought it, right? And so so water pollution is only an externality if the people who would enjoy it the most, for some reason, couldn't buy it, right? Because they couldn't afford to buy it, or so there's some impediment. But so long as the person that values that water the most buys it, either the factory dumping the pollution or the people that value it the most can buy it, then that would not be an externality. Similarly for air pollution, all right? So for air pollution, in some sense, for gases that are unregulated, like carbon dioxide, that isn't in the United States, that is an externality. But because basically if I'm emitting carbon dioxide into the air, I'm hurting people by emitting these things, but I'm not paying anyone. Nobody has the right, nobody has the property right to basically keep me from doing it. However, in other countries like Europe, where carbon dioxide is regulated, that's not the case, because somebody does have the right to keep me from doing it. The government basically says that if you want to emit carbon dioxide in Europe, if you're a power company, you have to pay the government for a permit. All right, and so that transaction where you basically pay the government, where someone owns a permit, that actually makes that that right to carbon dioxide polluting a property. And that actually makes that sort of, effectively eliminates the externality. The term we use in economics is that it internalizes the externality. And that's not just in Europe, right? For example, in the United States, actually most air pollutants are regulated, right? Sulfur dioxide, nitrogen oxide. If you're a factory, if you want to pollute these things, you need to buy a permit, or you need to, a lot, or if a lot of environmental effects you have. These are regulated. You need to obtain permission from the EPA to do these things. And so if these things are regulated, if permits are required, then they're not an externality anymore. All right. So the key point here is that something is only an externality when it is an effect that nobody has to pay for. All right. Another example of something that's not an externality is higher prices. Right. So people often say, that opening, rich people moving into town, making everything more expensive, that's an externality because all the prices go up. But no, prices by definition, even though that might hurt the poor people in living there, it's not an externality because the higher prices, well, that means that it's a price, right? Someone's paying for it. If a price exists, it's not an externality, because if a price exists, then that means the market exists, and if a market exists, that means the supply and demand is allocating those resources appropriately. All right, it's worth noting also that externalities are also not just positive, but they're also negative. Right, so we have not just negative, but also positive. So here we have positive externalities. Positive externalities are things that come about from economic transaction that benefit other people, where the person that created the benefit isn't compensated, right? He doesn't get paid for. For example, if I invent a new technology, I get paid for some of it, but to the extent that other people copy it for free, or benefit from the innovation, then if the people that aren't paying for it, that's a positive externality from innovation. Other kinds of goods that create positive externalities is if I create a park that anyone can visit, or if I plant flowers that my neighbors can see. Right? I get the benefit because I bought the flowers and I'm enjoying the flowers, but my neighbors who didn't pay for the flowers and aren't paying me for the right to look at the flowers are also getting benefits. But again, in the realm of positive externalities, there's also some things that people often think of as externalities that are not, right? So say I build a new factory into town and that creates all these jobs. People say, oh, that's a positive externality. No, it's not, right? A job is paid for, right? The price for a job is the wages you pay, and the company paying the wages for those jobs is basically paying the full value, the full value of those jobs. So jobs created are not externalities. All right. So hopefully, by these concrete examples, hopefully clarify the issue a little bit of what is an externality and what is not. So just to recap, now that we have some sort of concrete examples in our head, an externality is an outcome of an economic activity where property rights over the outcome are unenforced or undefined. By unenforced or undefined, that basically means that there's no market, there's no transactions, nobody's paying for those outcomes. And the reason this is important is because, if there's no market, then basically the fundamental welfare theorem does not hold, and therefore government intervention is justified. I want to take this moment also to just sort of point out the definition of a public good. All right, so a public good is really just a special type of externality. So it's fine just to think just to think of it as an externality. But people often use the term public good. In economics, what a public good is, it's a positive externality, and the reason it's a positive externality is that it's what's called non-excludable and non-rival. Non-excludable means that once I build it, say like clean air or national defense, I can't keep anyone else, I can't keep other people from enjoying the benefits of clean air or national defense. All right, and by non-rival, I basically mean that if one person enjoys national defense, having two people enjoy national defense, it doesn't hurt the enjoyment of the first person. Or clean air, right? So just if I'm enjoying clean air, then my neighbor can enjoy clean air without hurting me. All right, and so and the reason these things are externalities, especially not the excludable factor, is that because it's not excludable, that basically means that it's really hard to sort of charge you for the right to clean air, or it's hard to charge you for the right to safety from police, or it's hard to charge you for the right to be protected by an army. And so as a result, because I can't charge you for that, there's no market for that, and because there's no market for that, a public good is one more type of externality. There's, other types of externalities that are sort of more concrete. Economists tend to call these intangible externalities, and these often come up in the case of environmental protection. So, for example, one of these is basically the sadness someone feels when polar bears die. All right, or the sadness someone feels when a rainforest is chopped down. We talked about this in our earlier lecture about cost-benefit analysis and how economists try to measure the cost of these things. And in some sense, this is a real externality, and if we sort of follow the logic of externalities, these should be regulated so that we should stop people from chopping down rainforests if it makes people feel sad. We should stop people from killing polar bears if it makes people feel sad. On the other hand, you might also say that, and this is something economists don't deal with as well. Maybe the feelings are wrong. Maybe instead of stopping people from killing the polar bears, maybe we should just change how people feel. Maybe they should just get over it. Right, and maybe the thought of that sounds appalling to some people, but the same logic holds for other kinds of externalities, right? For example, the externality for the sadness someone feels when someone else gets an abortion, or the discomfort someone feels when a gay couple gets married. So, by the externalities logic, if a gay couple wants to get married but knows that it's gonna cause someone else discomfort, say one of those Republican candidates for president or something, then he should pay that person, right? That gay couple should pay that person because of the discomfort that they're causing. That's one argument. Or again, we could just say maybe they should get over it, right? Maybe it's easier to change people's sad feelings or discomfort than it is to sort of create more government regulation. All of the externalities discussion comes together when we start talking about the Coase theorem. All right, and the Coase theorem, sort of related to the fundamental welfare theorem, says that so long as property rights, exist and bargain is costless, then regardless of who has the property rights, efficiency is achieved. All right, and the idea here is that if we identify an externality, right, where then all we have to do is basically properly assign the property rights to any party, and once we've done so, then we're going to get economic efficiency, right? Because we basically completed the market, and now that the market's complete, we have the best possible outcome. All right, so to just sort of make this a little more concrete, imagine a factory and a few households where the factory would like to pollute. So imagine that the factory values the right to pollute at, say, $20, and that $20 is basically maybe the cost of installing a non-polluting technology. or the cost of disposing the waste in some other way. And let's say the households value the clean river at $25, right? So maybe $25 is the value that the households get from being able to fish in the river, or $25 is the value cost of the sickness that they would be forced to deal with from a polluted river. All right, so this is a case where as a society we would like it that the factory did not pollute, right? Because the people value a clean river at 25, the factory owners value a dirty river at 20, at the right to pollute at 20, and so society is better off by a net difference of 5 if we basically do not pollute the river. All right, so the way Coase's theorem works is to say, okay, well, suppose the factory had the right to pollute the river, then what would happen is that that the households would get together, they would pool their money, and they would pay the factory, say, $21 to not pollute, right? So the factory says, okay, well, should I pollute or not? I don't know. If I don't pollute, then it's going to cost me $20 to retrofit. But these households over here, they're going to pay me $21. So the factory says, okay, fine, I won't pollute. And the households, they're not quite happy, but they're better off they're better off because they don't lose this $25 of sort of benefit. And so in the end, the factory does not pollute. All right. Or the flip side of this is suppose instead that the households had the right to own the property right to the clean river, and in this case the factory, in order to pollute, would have to get permission from the households. In this case, because this socially optimal thing to do is not pollute, the factory owner would basically come to the households and say, hey, I'm willing to pay you $20 to pollute in the river, and the households would say, no way, right? The river's worth $25 to us. We'll let you pollute for $25, but nothing less. And once again, no pollution would take place. All right. A third possibility is we give the right to the clean river to somebody else, right? Let's call it the government, right? And the government, in this case, will say, okay, well, you got the two of you can bid for whether we should pollute or not. The factory says, okay, I'll bid $20 for the right to pollute. The homeowners will bid, say $25 to get to keep the river clean, and the government say, okay, household owners, you guys win. Give me $25, to the government, and I'll keep the river clean for you. All right, so no, in all three cases, regardless of whether the factory had the right to pollute, the right to decide what to do with the river, or the homeowners, or the government, all three of these cases, the same outcome is achieved. No pollution takes place, and sort of the total welfare in society is the same. It's important to note, though, that there is a big difference in terms of how good off people are, right? Because the property right to pollute in the river is an asset. When the factory owned the property right, the factory basically got bought off by the people, and the factory made lots of money. When the people owned the property right, the factory, basically had to eat its losses, and the factory had to lose the money. And when the government, had the property right, the government basically, was able to sort of charge permits and fees, and so the government made all the money. So, so who owns it has big effects as to who, how much money people have in the end. But in all three cases, the same economic outcome occurred. No pollution took place. It's worth noting also that the same logic would occur if, say, the factory valued polluting at 25 and the homeowners valued polluting at 20. Then in that case, the socially optimal thing to do would be to basically not, the factory should pollute, right? Because in this case, we're creating more economic value by polluting than by not polluting. And you might think, oh, how awful, the factory's polluting, but at the same time, the factory is, it's an enterprise. It's owned by shareholders. Shareholders is regular people. And we as a society should basically make sure that, we maximize the value created. Another way to think about this is that, the factory is creating economic value. As it creates economic value, that money goes to the government in taxes. It can then be spent on things like schools and arts and other things that we value. So as economists, we don't really care, how much, we don't really care how the money is spent. We just want it to be spent efficiently. And if it happened that the company valued polluting more than the homeowners who just really didn't care so much about the pollution, then we should allow the factory to pollute. At this point in my classes, there's always students, who raise their hands, who start to object, to say, oh, this is just more sort of right-wing conservative propaganda, right? That just says that, oh, we don't need government to do anything. All we basically need is, to assign property rights, and and government just sort of step out and let markets work. Well, actually, it's not that wasn't the lesson of Coase. If you go back and read Coase's paper from about 50 years ago, you find that Coase is well aware that this is an ideal world and these real markets rarely exist, and he actually points out why they often don't exist. Going back to our sort of polluting river example, right? The 4 reasons that Coase identified are basically, assignment costs is the first one. It basically means that even though it's nice in these little examples to say, oh, the value to the factory is $25 and the value to the homeowners is $20, in actual life it's really hard to sort of assign these numbers, right? We don't really know how much I value I value a clean river. The factory, may know how much it would cost to not pollute, but it's hard to know what's the value of a beautiful river, what's the value of health, what's the value of all these things. We can do our best, going back to our lecture on cost-benefit analysis, but it's definitely not easy. Another problem is what's called the holdout problem. So say, for example, that we give the households the right to the clean river, and, but say that, basically the households only value it at, say, $20, whereas right, so we'll say $20, whereas the factory values the polluting at $25. Then, economics and Coase's theorem basically says that we should allow the factory to pollute, right? Oops. So the factory works out an agreement where he's going to go to each homeowner and basically pay each homeowner, his share of the $20. All right, and so he goes, and so let's say he's going to pay the homeowner $21, so that each person gets $7. So he goes to the first guy, pays him $7. He goes to the second guy, pays him $7. He goes to the third guy and offers him $7, and the third guy says, hey, these first 2 payments were sunk costs. He's already paid them off, and it's still worth the factory $25 to pollute. So this guy knows I could demand up to $25, and the factory is still gonna, is gonna be willing to pay that up. That's sort of called the holdout problem, right? You often see examples of this where basically a developer is trying to build something, and often it's the very last house that basically is demanding really, really high, payments to get bought out because he knows he could hold out for it. All right, and so the problem with this is that is that the factory anticipating this is just not going to try, right? He's going to know that, if I may have to pay the first 2 guys $7, but the third guy's going to charge him $25, and so the total charge is going to be far more than it's worth it for him to pay, and so as a result, an economically efficient transaction does not go through. All right, another similar example is called the free rider problem, which is, say we reverse this and say that instead at the household it's worth $25 for the households and $20 for the factory. All right, in that case, in that case, what happened? What gives a free rider problem, where basically the households all agree to chip in, say $7 each, to get the factory to stop. The thing is, though, that if there's enough households, then each household will think, okay, well, I don't have to chip in if everybody else chips in. And if everyone sort of thinks that I don't have to chip in if everyone else chips in, then in the end nobody chips in, right? This is the example of sort of, say, public radio. This is the example where if everyone sort of thinks that someone else is going to take care of it, nothing happens. Everyone free rides, and again, the economically efficient transaction of stopping the pollution in this case does not go through. All right, the fourth and final reason that Coase sort of gave why Coase's theorem might not work is that there may be just transaction costs, right? It's expensive to write the contracts and hire the lawyers and have all these fees of sort of making all these contracts to work. So as a result, maybe it just in the end, these negotiations just can't go through. All right, so as a result, the government, there is a role for government, and Coase fully acknowledges that there's a role for government to step in and basically decide where the property right should go to. Right, the government can sort of do the math and say, oh, well, in this case, the homeowners value the factory more, so we'll just give the homeowners the rights to to decide what to do with the river. All right, or in another case, maybe the government will decide the factory, values values the river more. In that case, the factory should basically decide. Or a third case, it might just be easier for the government to basically own the rights, and for the government to sort of regulate or regulate who, how the river is used, or basically sell permits for how the river is used. So all three of these possibilities of basically the producer, the consumer, the government having the property rights is also a way to sort of get to achieve the optimal outcome. We could tie this discussion in what we know about supply and demand. All right, so recall that supply and demand is sort of plotted on this graph with sort of price here and quantity here. All right, and what we know is that when we're plotting supply and demand, there's going to be a supply curve that looks like this, and the supply curve represents sort of the marginal cost of production. And there's going to be a demand curve that looks like this, and the demand curve represents the marginal benefits of consumption. All right, the problem that occurs with externalities is that with externalities, there's actually the cost curve that companies face is not the full total cost, right? So this is the cost curves this is the private supply curve, right? And the reason this is problematic is at the point of the private supply, at the point where private supply meets demand, we're actually the firm is not basically fully accounting for the full cost of its production, right? If it were accounting for the full cost of its production, it would be up here at a cost curve higher than the private supply curve, and that's because these additional costs are things like the pollution costs. These are things like noise pollution or air pollution or water pollution, right? These additional costs are costs that the company didn't have to pay for. If they had to get a permit if they had to get a permit to pollute in the air, then in that case, these two curves would be the same. But if they didn't have to get a permit and they could pollute the air without being held responsible to polluting the air, then you get this gap between the actual supply curve and the private supply curve. And what that mean? What that basically means is that in markets where there's externalities, the price here, the equilibrium price is going to be lower than what it should be, and the equilibrium quantity is going to be higher than what it should be. All right, so the equilibrium price and quantity should be up here, but the equilibrium price and quantity should be, but in fact it's actually up here. It's actually down here where the price is too low and the quantity is too high. All right, so fortunately, there's an easy way to fix this. Make them pay. Right, and the easiest way to make them pay that economists all like is basically charge a tax. If we basically just charge a tax on the producers equal to the size of the externality, that basically is that basically forces the private supply curve up to match the actual supply curve. That's going to raise the prices of the goods, going to lower the quantity consumed, and in the end, we're going to sort of get to the efficient market outcome, which is right there. See, the reason why we're at this is that the reason why the private supply curve is inefficient to begin with is because this is the point where the benefit of consumption is here, the cost of consumption is up here. So these are all points where the cost of consumption is higher than the benefit of consumption, and these are points where basically cost benefit is not being observed. Right? That's why we want to get back to here, where the costs and benefits are exactly equal. Oh, one other thing to notice is that when there's externalities, you have two problems, right? Both the price is too low and the quantity is too high. And so, the tax, what the tax does is the tax basically raises the price so that the price is equal to the right price, and right, like this. and it basically raises the price, so the price is equal to the right price, and once the price goes up, the quantity will adjust accordingly. That's another equally reasonable alternative is that the government can put a cap, can put a regulation, a quantity control. Because if the quantity is too high, the government gets to sort of say, okay, well, you can't produce that much, you have to produce less. You need a permit for production. All right, and that'll bring the quantity down, and once the quantity goes down, the price will also adjust, and the market will fix itself either way. This is essentially the debate in climate discussions between, should we have a tax on carbon emissions or a cap and trade system on carbon emissions, and we'll discuss that in a lot more detail in the cap and trade lecture in a couple weeks. But I want to issue a warning before you think that's great. Right? Oh, so government just has to sort of identify the externalities, put the appropriate tax or regulation on there, and all of a sudden, everything's perfect. The problem is government can make mistakes. All right? So, I think Winston Churchill had this nice line that democracy is the worst system he knows, except for every other one. It's basically, one of the great economists, Ken Arrow, has basically proven mathematically that democracy is fundamentally flawed, right? Mathematically, mathematically, there's going to be lots of policy choices that are made in a democracy that are just, bad for everybody. And so, we should be careful when we sort of say the government can sort of fix everything. The other reason why we should be aware of sort of too much government interference is that, there's added transaction costs, right? So every time you want to, create, new permits or new fees or new regulations or new taxes, that's going to require hiring lawyers and fee collectors, which means lawsuits and juries and all these other transactions that, that in the end may be more costly than the externality you're trying to fix. And then the final thing is that magnitudes matter, all right? And this is a mistake that even economists make, where they sort of say, oh, yes, air pollution is bad, therefore we should do something. But it's important to sort of measure how bad, right? Because, maybe the total cost of air pollution for some new chemical called, I don't know, tetrahydrocycline, yeah, it sounds scary, but maybe the cost is only $10, right? So maybe we should, instead of creating new regulations, we should deal with it. Or maybe the cost of this new pollutant is billions of dollars, in which case we should do something. But the key thing is it's really crucial to sort of measure how big the externality is before we just sort of decide how we should sort of go about handling it. For example, a question that often comes up is, how guilty should you feel from driving your car? All right, and we know that driving your car burns gasoline. Gasoline has lots and lots of externalities. And so people say, oh, we should buy a hybrid car, or you should buy a bicycle because, you're doing all this damage. Well, the truth is that we can measure how guilty you should feel. All right? And the number that I sort of like, which comes from this paper, which is by Perry and Small in the American Economic Review in 2006, is about $1 of guilt for every gallon of gasoline you burn. And Perry and Small get this number from adding up a number of different effects. This is 5 years old, so 6 years old now, so it might be a little bit dated. The numbers might be a little bit higher, but the intuition is about the same. They basically they calculate the environmental effect of burning gasoline, and they find that each gallon burns contributes to global warming by about 7 cents of damage, and contributes to other types of tailpipe emissions like sulfur that sort of leads to asthma. So all that told is about 21 cents. Also, driving also creates traffic, and so by creating traffic, by creating traffic, we basically create about 22 cents of sort of externality on other people in terms of time they're wasted, stuck behind me in traffic. Also, driving is basically creates traffic accidents. So every time I drive, I basically, I have some chance of crashing into somebody. That's 11 cents. These next two are very speculatory. But if you want to say but I think Republicans especially are worried about the national security concerns for gasoline. So, various estimates sort of say that because we, use so much gasoline, we have higher security costs in the Middle East. And so, some very rough numbers that people have put out there is basically 20 cents in terms of budgetary costs for military spending in the Middle East. And another, say, 25 cents per gallon due to international relations or diplomatic really we have no idea, but I just sort of picked 25 cents here because it leads to a nice round number of $1. All right. And it's actually also, we should be noted that we're already paying for some of this damage that we're doing. All right, so the current average tax in the United States for gasoline is about 41 cents. So actually the only additional damage we're doing by consuming gasoline is about just 60 cents more. All right, so now we have this number, 60 cents, right, for the amount of extra damage we're doing to the environment by buying gasoline. And now the question is, okay, so how guilty should I feel, or how good should I feel about myself for biking to work instead of driving? All right, so say I'm, basically indifferent between driving to work and biking to work, but I want to do good. I want to feel good, do good for the environment. So I'm going to bike instead of driving, and so say I save a gallon of gas each day by biking instead of driving. Well, then you should basically feel about 59 cents of goodness about yourself, right, for biking. That's how much you help the world society by biking instead of driving. And that's valuable. Every gallon saved is good. But I guess it's important as an economist to sort of point out that there's lots of ways to sort of, feel good about yourself. And if biking is only going to produce, say, 59 cents of value a day, maybe there's other ways you could help out, right? Maybe instead of, biking, you could basically, work for a charity or a soup kitchen, or donate, or work an extra hour at work and donate that money to planting trees, right? All of which will also produce probably a lot more value than 59 cents. Or maybe not, right? That's your decision. And the point of this is basically that we can measure how much damage we're doing when we do things like drive a car. And, and by measuring, then we could decide, are the costs really worth it? Okay, so that was a lot of information, and a lot of it was pretty abstract, so thank you for sticking with me. Hopefully these first introductory lectures will give you a solid grounding on the theory of sort of energy and environmental economics. And if you've stuck through it all, I think you'll be happy to know that the remainder of the course will be sort of much more practical and much more applied. You'll sort of see how all this is used. All right, so the next lecture will be about the science and economics on the current situation regarding climate change. Then we'll talk about the proposed economic solutions, and then we'll sort of talk about the various technologies that could come about in response to climate change and how economists sort of think about them. Thank you very much, and I hope to see you next time. Welcome to the Udemy Energy and Environmental Economics lecture on the effects of climate change. For those who have been with me since the beginning, thank you for bearing with me through some, sort of rather theoretical, abstract stuff. Hopefully that'll give you the framework and background for understanding the next series of lectures, which is going to be rather more applied. And for those of you just joining me now, I think it should be fine. We're going to sort of deal into how economics can help us think about climate change, right? So oftentimes, the climate change, I agree, is one of the most important issues of the 21st century, and oftentimes you sort of hear the scientists debating it, the business people debating it, the politicians debating it. What you don't hear enough, I think, is how economists sort of picture climate change. So, so I think that one of the main motivations for me for doing this course is to sort of introduce the economic perspective in thinking about these issues. Today we'll be focused on sort of the science of climate change. As always, this is Ben Ho, an economics professor at Vassar College, and thanks for coming along. So the majority of this lecture is going to deal with this question of, what is the scientific basis for our beliefs about climate change, or more generally, this question of does, man-made climate change exist? So, this was an op-ed I pulled out of the Wall Street Journal, and it's emblematic of a lot of things that, say, especially Republican politicians have been saying about how global warming is just another panic that's been invented by the media or invented by sort of pointy-headed elites, and that there's really nothing we should be worried about. I want to say, first of all, that, I'm an economist, not a scientist. I have read a lot of the science. I've, read much of the 1,000-page United Nations IPCC report on this question, and I'm going to sort of tell you what they say. But, I do want to point out that reasonable scientists have, dissenting opinions. And I'll tell you, what I believe and what I interpret as a scientific consensus. But, I think it's worth pointing out that, what I believe and probably what you believe is oftentimes a sort of arbitrary, right? what you believe just comes from, what you think scientists believe, or what you read in newspapers, or from, or books, or, TV shows. And the people that disagree about climate change also sort of read the same things. And so before people are sort of so dismissive as to opposing views, I think it's worth this, take a second and sort of consider, where do your beliefs come from? Why do you believe the things you do about science, about global warming, about economics? So this is sort of the standard argument that people sort of show to point out that climate change exists. This is, how Al Gore starts his movie, An Inconvenient Truth, right? He basically plots two records that look at, the Earth's temperature over the past 140 years, and it sort of follows this upward path. And then he looks at the plots along the same time of human carbon dioxide emissions over the past, 140 years, and it sort of follows the same path. And he says, voila, proof that, carbon dioxide causes climate change. All right, first thing I want to point out is this is I think the stupidest evidence ever presented anywhere. The most basic the most basic statistical fallacy is that correlation is not causation. All right, and that just because something has a positive time trend doesn't mean it causes something else as a positive time trend. Lots of things increase over the past 140 years, right? Including, I don't know, the number of people named John in the world, the number of books published, the number of, things just increase. Lots of things have a positive time trend over time. That doesn't prove that they cause something else. And so this, I think, is just ridiculously specious evidence. However, I want to emphasize firmly that I am totally in the camp that, man-made climate change does indeed exist. All right, I used to work for the Bush administration, and I think despite popular belief, even the Bush administration believed in climate change. Here is this, quote from June 2001 that fully acknowledges that the National Academy of Science indicates that that the increase in temperature is due in large part to human activity. All right, and so and that the United States recognizes the responsibility to reduce our emissions. So even though there's probably lots of crazy voices out there and lots of people with interesting views, I think the people that sort of studied this, the people that looked into this, the people that looked into the science, generally believes that climate change exists. All right. All that being said, though, there's some key caveats about interpreting the science of climate change. Yes, the world is getting warmer, but before we decide what to do, the science is not enough. All right, and so one thing I want to point out in this lecture is, why is it that people think the Bush administration didn't care about climate change? Why is it that where did this perception come from? And I argue that this perception came from the fact that scientists do not understand economics, and that scientists and economists together often don't understand politics. And it's this combination of these three things, right? The science, the economics, and the politics that are necessary to fully understand, how climate change is going to impact society and what we should do about it. And that, people coming at this from just one point of view alone, so say from the scientific point of view or the political point of view, often misinterpret the motivations of the people that they disagree with. All right? So even though the Bush administration, often took a wait-and-see approach to climate change, it didn't mean that they're anti-science. It just meant that maybe their preferences are different in terms of what we should do about it. But I want to emphasize again that I agree with the scientific consensus, right? That mankind is contributing to climate change, and I think most of the papers, if you read the United Nations reports, they make a compelling point. However, I think it's really easy for people to overstate the case. All right, so if you really carefully read the United Nations reports, they basically say that man-made global warming is very likely. All right, so that's fine. Basically that means that if you read the footnotes, they think that they're 90% sure that humans are causing global warming, but that also means they're 10% unsure. Right, and quite reasonable to say, okay, why don't we wait 10 years to take a wait-and-see approach, because there's this 10% uncertainty, right? The policies that people are going to advocate to stop climate change cost trillions of dollars, right? The budget debates in Congress these days, they're in the billions. They're like a tiny fraction of the cost that global warming policy could entail. And there's a 10% chance, according to the scientists, that this may all be for naught. So it's perfectly reasonable to think, okay, maybe before we sort of commit trillions of dollars to attacking climate change, to sort of do the best we can to sort of reduce this 10% number to something even smaller. All right, the other thing to sort of point out is that if you read these United Nations reports, right, the IPCC estimates that sea level rise in the next 100 years is going to be something like 18 to 58 centimeters. All right, so yes, these estimates are old and they've revised them over time, but think about 18 centimeters, right? This is not very tall. All right, and yes, it's going to cause problems, and people that live by the ocean, they're going to suffer erosion, but it's nothing we haven't dealt with before. One question I often ask students in class is, how do you think this 18 to 58 centimeter number compares to, how much sea levels have risen in the past 100 years? And the answer is it's about the same, right? I think sea level rise in the past 100 years has been around 20 centimeters, and yes, there's been flooding and there's been problems along the coast, but nothing that you've noticed, right? No one's, there's nowhere in the history books that we talked about the catastrophic sea level rise for the past 100 years. And the next 100 years, there's going to be more of the same, all right? Maybe somewhat more, but again, we shouldn't exaggerate. Temperature rises, this number's been revised a bit here and there, but in the report was 1.8 to 4 degrees Celsius. Yes, warmer, and yes, there's going to be consequences, but it's important to be, it's important to sort of be careful with, not exaggerating. The other thing is that people sort of talk about the potential for, for actions we do today to sort of last for all eternity. And yes, there's, yes, maybe that's true, but the science of that is not entirely clear cut. All right. And there's some estimates that sort of say that excess carbon in the atmosphere has a half-life of, say, 25 to 100 years, right? The models are a little more complicated than that, but that basically means that, if we sort of dump a lot of carbon dioxide in the atmosphere and wait 100 years or so, which admittedly is a very long time, but we could conceivably wait 100 years or so, then that carbon dioxide, might go away. All right? So, so I think it's important again to sort of say that it's not the end of the world we're contemplating. It's not the flooding of the Statue of Liberty. We're talking about 18 to 58 centimeters on a problem that, might last 100 years or so, which is big, but not too big. All right? All that being said, though, there are important sort of nuances to this argument, right? One important nuance is that are going to be winners and losers. All right, I think part of the in the next lecture we'll look at the economic consequences of climate change. You'll find that in places like Siberia, Canada, cold places, people are going to win out, right? There's going to, it's going to be warmer there, and people are going to be happy. Whereas in hot places by the tropics, say Sri Lanka or Bangladesh, they're going to be losers, right? They're like close to the water, and it's hot, and it's going to get even hotter, and they're going to lose out. And we should address that issue as we think about the right policy. Also, in terms of winners and losers, yeah, there's going to be more people dying from heat, right? There's going to be more sort of tropical diseases. But there's also going to be fewer people dying from cold, right? There's going to be fewer, so in general, more people die from the cold each year than from the heat. So it's going to be warmer. That means, less, hypothermia, less, flus, less all these things that sort of depend on cold weather. So it's important to sort of be aware of those trade-offs as well. It's also important to sort of be aware of the fact that these are average effects that people estimate, 18 to 58 centimeters, say 2 to 4 degrees, but there could be catastrophic effects that I'm not accounting for. All right, and so so basically, people sort of talk about the fact that maybe there's certain tipping points that we may reach if we're not careful that are going to sort of lead to sort of seismic shifts. I think that's really possible, but also the science is less well established on that, and we should be careful not to exaggerate, what the science actually says. But I do want to encourage you to read the IPCC document, right? The IPCC document is basically, a summary of that the United Nations put together that won the Nobel Prize on sort of summarizing the effects of climate change. It's a long 1,000 pages to slog through, but if you're really interested, that's where you want to go. One warning, though, is that they offer summaries for policymakers and sort of condenses that 1,000 pages of details into like a 10-page, 20-page summary. That's fine if you want to get started, but that detail omits lots of important information, and it's really easy to be misled by those 20 pages. So if you really want to dig into it, I encourage you to dig deep. Here's a little bit on sort of the science of, the carbon cycle. So this section over here, these two lines represent human emissions in black. The width of the arrows represents just the relative quantity of those emissions. And in some sense, people say that we shouldn't worry about human carbon dioxide emissions because it's a relatively small part of the carbon cycle compared to the massive amounts of carbon dioxide being exchanged, say in the oceans up and down, or in the forests up and down. basically the human component is relatively small. To that I say, that's a way oversimplification, right? Nature is in a delicate balance, and the models sort of say that even these sort of small additions from mankind could have big effects on the balance. And me being an economist and not a scientist, I'll take their word for it. One thing though I want to point out in this picture that I think sort of blew my mind when I found out about this is that we were always misled about one part of the carbon cycle, I think, which is this idea of the role of forests in the carbon cycle. All right, so I think, so this is going to be relevant when we think about, the role of planting trees to sort of, stop carbon emissions. I was always taught, at least in, middle school or elementary school biology class, that trees eat up carbon dioxide, right? That trees sort of take in carbon dioxide from the atmosphere and convert it into wood and convert it into food and, emit oxygen for us to breathe. All right, and in some sense, so that the trees are basically this part here. And in some sense, that's true, but the wrong extrapolation from this is that forests eat up carbon dioxide, and that is fundamentally not true. All right, and so this is sort of a mind-blowing thing. But if you think about it, if forests constantly was eating up carbon dioxide in the atmosphere, all that carbon has to go somewhere, right? It can't just do this forever, or it'll just keep on growing forever and forever and forever. And what happens in a forest is that at some point trees die, right? And depending on the species of the trees, but after 10 or 100 years, the trees die, and when they die, all the carbon that was sort of sucked out of the atmosphere to make the tree dies, it decomposes, and it gets put right back in the atmosphere. All right, so all this carbon dioxide that's been being sucked in through photosynthesis, all of it sort of comes out again, because of forest and equilibrium. For every tree that grows up, another tree is dying at equal rates. And so, so I think something that sort of blew my mind is that a forest really is not sitting there eating, taking carbon dioxide out of the air for us. The better way to think about it is that to think about it as like a battery or as a storage container for carbon dioxide, right? That all the carbon dioxide that might be in the air is stored temporarily in these trees, but then eventually, if you just wait long enough, the trees will die and they're going to go back in the atmosphere again. And so this will be sort of relevant later when we discuss what are possible solutions, because I think planting trees is going to be a big part of the solutions to climate change, but the effect of planting trees is going to be subtle. Here's just some background on where carbon dioxide emissions come from within the United States. You'll see that the vast majority of it is coming from energy. All right, you see that some smaller part comes from agriculture. This comes from the famous cow methane, cow gas, for example, and other agricultural processes. You see some small part comes from industrial processes. Some small part comes from from waste, decomposition of landfills, and some tiny part comes from sort of cutting down trees. Even though what's notable is that within the United States, actually trees are actually taking carbon dioxide out of the atmosphere on net. Right, and on the whole, I think what people don't appreciate is that the United States is actually increasing its forested land area every year, as the United States sort of replants all the trees that were cut down during the Industrial Revolution. And this is a process that we can accelerate to sort of help mitigate carbon dioxide emissions. But at the same time, it's important to note that when we're thinking about doing something about climate change, it's important to think about energy, because that's, at least in the United States, it's by far and away the primary source of emissions. So looking at, so sort of taking the energy component apart and seeing where all that energy emissions comes from, basically, sorry, let me get my arrow. So basically the two main, components of it, one is basically going to be transportation, and this is pretty much all oil, right? So if you think about it long enough, you realize that almost all our transportation, whether it's planes or cars or trucks, almost all of it comes from oil or gasoline or diesel or jet fuel, right? All come from the same place. Electricity we get from a lot of different sources, right? The two biggest sources are the biggest sources are coal, natural gas, nuclear. You'll note that nuclear basically is responsible for almost no carbon dioxide emissions. Most of it comes from coal, right? So about 40% of the U.S. electricity comes from coal, 20% comes from natural gas. You'll note that even though a substantial amount of electricity comes from natural gas, it's responsible for a relatively small chunk of emissions, right? Because natural gas burns relatively cleaner, it's more efficient than coal, and so as a result, basically, all the moves in the past few years to move toward a more natural gas-based electricity generation economy is going to reduce CO2 emissions in the long run. The other thing that is important to be aware of is as people sort of talk about renewables as the solution to all our energy problems and the crazy fast growth they've been undergoing. I think that's totally true, but that's because they've been growing from really small baseline, all right, and they're still a really small part of the world energy system. So in this pie of all the sources of energy the world uses, renewables make up 13%, which is sort of respectable. But of that 13%, almost all of that is from either hydroelectric power or biomass, which in the world context is basically just burning wood in a stove. All right, the renewables that we think about when we think about sort of the future of renewable energy, like tidal power, wind power, solar power, geothermal power, all of that is really just this tiny sliver of this tiny chunk of the entire world energy supply. And so it's growing, and it's great, and it's growing really, really fast, but it's basically just taking one tiny sliver and making it two tiny slivers. And so there's a long way to go before renewables can be a significant part of replacing the world energy usage. The other key thing to be aware of is that carbon dioxide emissions are a global problem. The United States is a big chunk of it because it's it represents about a quarter of the world GDP and therefore about a quarter of emissions today in 2010. But recently, China, overtook the United States to become the world's largest emitter. And as we move forward, China is only going to be growing in importance in terms of emissions. And so, an important part of this is that even though U.S. is a big emitter, it's going to be a relatively, it's still a small part of the whole global picture, and that therefore efforts to cut emissions within the United States only make sense if there's also equal cuts, across all the different countries in the world. Finally, I just wanted to put a note on methane, which is normally not that important because, but I want to talk about it because some people have sort of said that people have focused wrongly on carbon dioxide because methane is actually 23 times more potent in terms of the global warming potential. Okay, that's sort of true, but there's important caveats there. Basically, methane emissions are 300 times lower than carbon dioxide emissions, and so on the whole, it's much less important. And then also, methane has a relatively short half-life in the atmosphere, right? Sort of less than 10 years compared to carbon dioxide with a half-life of 100 years or more. And so, as a result, even though it's potent, there's not a whole lot of it, and it sort of fades away. And so, except for a few sort of subtle examples, I think the people, say in super freakonomics, that sort of say that methane is the real culprit, it's sort of misguided. All right, so that's the sort of whirlwind tour of, I think, this is sort of the scientific background of climate change, where it's coming from, and sort of the scientific effects. Of course, this is by no means comprehensive. I'm an economist. I'm just trying to focus on the details that are going to be relevant to the economic analysis. I encourage you, to go out and and read the IPCC reports or look for more details on your own. Put questions in the discussion board. I'm sure there's a lot of people dying to complain about things I've said. I encourage you to do all that. But again, I'm an economist, and so I want to spend most of my time focused on the economics, and that's what we'll do in the next lecture. All right. So for the next time, we're going to consider this proposition. The proposition is simple: it's that the problem of climate change is so big, we should do everything we can to reduce emissions. And to sort of give these things in terms of everything we can. What do I mean by that? Here are just some examples of policies that people have advocated to reduce emissions. The top 7 over here, these are policies sort of advocated by Al Gore in An Inconvenient Truth. And these are just other policies I've sort of pulled from newspaper articles and clippings that people have advocated. And we're basically going to sort of evaluate these policies through the lenses of economics in the next lecture. Thank you very much, and I look forward to seeing you then. Welcome to the second of the climate change lectures here as part of the Udemy course on energy and environmental economics. As always, this is me. This is me, Ben Ho, assistant professor of economics at Vassar College, here to sort of walk you through the economics of how we should think about the policies of climate change. The focus of this lecture is to sort of thinking about the effects of climate change and how, as economists, we measure those effects. So here's a proposition that a lot of, especially environmental activists, but a lot of people in general sort of just take for granted. And that's this idea that the problem of climate change is so big, underlined so big,
that we should do everything we can to reduce emissions. When activists sort of like Al Gore talk, they talk about, all the calamities of, I don't know, animals going extinct and shorelines changing and, and people dying and, the Arctic melting. And I don't know, dogs and cats playing together. So all these huge calamities, and it makes you think, and it makes this proposition sound very plausible. All right, and what I hope to convince you of in this lecture is that economists who have sort of studied this actually disagree, and so we'd actually sort of rephrase this question in a slightly different way. So right here is just a list of some of the policy proposals that are sort of out there for dealing with climate change. Things we could do to sort of slow down the change in climate and maybe even reverse it. We'll hopefully spend the course of this lecture sort of learning the tools to evaluate these different policy ideas. These 7 up here I sort of picked out because they were the 7 policies listed in Al Gore's film. A couple of these are sort of relevant today. So Al Gore's film, An Inconvenient Truth, just a few days ago, basically, the EPA actually implemented the first one, of banning new coal power plants until they sequester emissions. In the past few years, under both the Bush and Obama administration, this one sort of come to pass as well. The ban on incandescent light bulbs was passed, but I think so far, Congress has been trying to stall that. So a lot of these policies have actually come into effect, but I think it's important to sort of take a step back and think, were these a good idea, and should we try to do more of it? These policies down here are just some policies I picked out of newspaper articles that people have been thinking about. There's a campaign at Vassar now to ban bottled water. Japan implemented campaigns to ban air conditioning. A lot of people are pushing hybrid cars. A lot of people are pushing local foods. How should we think about these different policies? I want to contend that the right idea of thinking about policy is not that we should be doing everything we can. The right question to ask instead is, what are the benefits what are the costs of reducing 1 ton of carbon dioxide, and compare that to the benefits of reducing 1 ton of carbon dioxide, by these methods, and basically use that to evaluate which policies are good ideas and which policies are bad ideas. All right, of course, we can still go back to lectures 2 and 3 that talked about the merits of cost-benefit analysis, right? And it's worth thinking about. Does cost-benefit analysis make sense? What are the limitations? I think that's entirely fair. But once you've convinced yourself that cost-benefit analysis is a reasonable approach, it becomes a powerful tool in helping us understand policy. One thing I want to point out, so I'm going to focus our discussion talking about tons of carbon dioxide. Oftentimes you'll find confusion both by policymakers and journalists when people sometimes talk about tons of carbon or tons of carbon dioxide. These are basically just 2 different unit measures of exactly the same thing, right? So for those of you that remember high school chemistry, when we emit carbon dioxide in the atmosphere, right? Basically, we could either measure the total weight of all the carbon dioxide, or we can measure the total weight of just the carbon atoms themselves. These give slightly different numbers, but the intuition is going to be the same no matter what. I just wanted to give you guys a heads up in case you sort of read more about carbon dioxide and prices of carbon dioxide in the future. So the 2 main methods of sort of measuring the benefits of climate change mitigation. The first is basically calculate how far reducing emissions by 1 ton moves you toward a specific goal. All right. For example, a lot of activists are claiming that we should sort of stabilize concentration of carbon dioxide in the atmosphere at 550 parts per million. All right. That's one way. I think the economists sort of prefer the second way, which is to sort of calculate the cost avoided by reducing those emissions. All right, which is basically we sort of calculate how much what the impact on the environment is going to be from those carbon dioxide emissions. Calculate the impact of that on the economy, on human welfare, and basically go from there to see how much damage your ton of carbon dioxide is doing. It's important to note that when we do this, these numbers are not going to be as big as we've been led to believe. All right, so there's still a lot of uncertainty here. But Bill Nordhaus, probably one of the most likely winners of the Nobel Prize in this field one day, basically at the National Academies of Sciences, calculated that the best estimate for damage, it roughly is 0 plus or minus 2.5% in terms of current human welfare. All right, so 2.5%, again, is that big? In some sense, it's really big. 2.5% of human welfare is billions, if not trillions of dollars, but it's only 2.5%. All right? One estimate that people sort of cite a lot is that, if climate change is left unabated, it's going to cost the world economy $304 billion by the year 2050. Now, again, $304 billion, that sounds really big, but, today's economy is a $50 trillion economy. $304 billion is noticeable, but not that big. In 2050, the economy is going to be quite a bit bigger than it is today. So, again, it's important to keep these numbers in context, and these are not disaster movie numbers. So there's, sort of two sets of methods economists sort of use to sort of come up with these numbers. One of them is basically just to, try to add up the impacts of climate change. So what we do is we sort of go to the scientific evidence and sort of see, okay, what do the scientists predict about the impact of emissions on things like temperature changes, on things like rainfall patterns, on that kind of thing. And then we basically go to these big computer models, and we sort of add up, okay, what's the impact of those temperature changes and rainfall changes, and I don't know. And sort of other climate changes on things like on components of GDP, like agricultural goods, transportation, shipping. Agriculture is the main one, right? Agriculture is still a main part of the world GDP, and I think climate's got to have the largest impact on that. But we also add up sort of other ancillary effects, such as the impact on coastal protection. Things like. Recall that the central estimates for the impact on global sea level was going to be something like 20 to 50 centimeters. So again, not a huge amount, nothing we haven't dealt with in the past, but something that's going to have tangible costs. We can calculate what those costs have been in the past and sort of use those to extrapolate what those costs might be in the future. And then finally, sort of add up the value of other health and environmental impacts. Things like the effects on tropical diseases, things like the effects on sort of parks and ecosystems that humans depend on, and we sort of go and apply the techniques from lectures 2 and 3 on cost-benefit analysis to sort of add all those things up. All right. Another similar impact is just to look at the past. Similar analysis is to look at the past effect of past temperature variations on things like on GDP, on production, on productivity, and use that as a baseline for measuring the economic effects of carbon dioxide emissions. One really important part of this analysis that I think especially the activists often forget is that there are actually substantial benefits to global warming that people don't think about. All right, so among them, more people die from extreme cold than extreme heat. So as the world gets warmer, some countries might need more air conditioning, but and yes, people die from extreme heat from heat waves, but in the future we expect most people to have air conditioning. But we have fewer people dying from extreme cold as well, and that's something to worry about. The flu virus happens in winter because it's colder then, and so diseases like that are going to have a smaller effect in the future. I think the other important thing to think about is that some parts of the world are colder than they probably like to be, right? There's going to be, substantial benefits in colder countries like Russia and Canada that, we should be, who might be thankful for the effects of global warming. So I'm not saying that it's, that these benefits are going to outweigh the costs of global warming. Actually, in some cases they actually do, but I'm just going to say, but I think the main thing to be aware of is that global warming is not the unmitigated disaster activists want you to believe it is. Here are the results of a meta-analysis put together by Toll in one of the main economic journals out there. So I think this is probably considered, one of representative of the economic consensus of how economists sort of see, predict climate change is going to be. Basically, what this chart says is that for different predictions about future temperature, right? Either 0 degree change, 1 degree change, 2 degree change, 3 degree change. What's going to be the effect on GDP in terms of, or just welfare generally, right? Measured not just in terms of economic productivity, but also in terms of things like diseases and coastal impacts and that kind of thing. And the dots sort of show the central estimates. All right, and the bars sort of give you a confidence interval. And what this sort of shows is that actually the central estimate says that if for 1 degree of global warming, actually human welfare could increase, right? Just because, again, we'll have, more agricultural production in countries like Russia and Canada, fewer diseases, all those, fewer cold-related diseases, all those things. And so in that sense, 1 degree of global warming we should look forward to some extent. All right, and of course it's possible. So as temperatures get higher, and I think more and more estimates say that as emissions get worse and worse, the expected impact is going to be higher. Is going to be higher than 1 degree. That's fine. But if we look at the effect, it's not that different from zero, right? That the central estimate for a 2.5 degree effect on warming is close to zero, and this, maybe down to negative 2 to 3% confidence interval. Well, the important thing to be aware of, though, is as we get to 3 degrees, right? Then the numbers start getting lower and lower, and the risk starts getting higher and higher, and it's sort of the combination of the risk of higher temperatures and this huge uncertainty that we should start thinking about in terms of assessing the economic impact of climate change. All right, and so just like we talked about the tricky issues of cost-benefit analysis in the earlier lectures, I want to talk about them again here. Right, one is what discount rate do we use? Like, how should we evaluate the impacts of our children versus the impacts on our grandchildren? People often say that, oh, we should take care of our grandchildren and because they're sort of cute and adorable, right? But actually, from an economics point of view, our grandchildren are basically going to be spoiled, right? They're basically going to be several times richer than we are, right? If you imagine the average standard of living we have today, that number doubles every, say, 20 or 30 years globally, all right? And so if we think about people living 30 years, 60 years, 90 years in the future, they're going to be 4 times, 8 times richer than we are. Why shouldn't we let them deal with these problems instead of us? I'm not saying we should, but these are important questions that we have to think about when we think about how do we evaluate these cost-benefit questions. Inequality is a big issue to worry about, right? We talked about the problem of gamma in earlier lectures. One of the unfortunate effects of climate change is that it's going to benefit relatively rich countries, right, like Canada and Russia, and it's going to hurt a lot of sort of relatively warm and poor countries that lie in tropical areas. Bangladesh is one that sort of people working in this area bring up a lot because it's one of the poorest countries in the world per capita, and it's also relatively low lying and close to the ocean. So I think that's something that we have to think about in terms of interpreting these numbers. What about things we can't measure? So basically, in terms of how these numbers are generated, it tends to be generated based on numbers that are sort of more more based in economic transactions that are measurable, right? Things like agricultural output, things like value of land, that would be destroyed, all right. Whereas sort of the fluffier things that we talked about earlier, like the value of a polar bear's life, they tend not to be included, and so maybe that would sort of change. Would change how you interpret these numbers. The fourth thing that that's a tricky issue is that these make huge assumptions about technology, right? We're trying to make predictions about what's going to happen 50 years down the line, 100 years down the line. How do we even conceptualize what that is, right? If you just think about technology that's progressed over the past 50 years alone. 50 years ago, we barely had DNA. We had no computers. We had no internet. It's hard to imagine what kind of technology might show up in 50 years that's going to totally change all our thinking along these lines. And so I think that's another reason to be suspect for these analysis. A fifth thing to be worried about for these analyses is how do we account for uncertainty? You saw there's rather large error bars, right? And there's potentially a big difference between a negative 1% change and a negative 10% change. And how do we know that might not happen? What you might notice is that the errors especially skewed downward, right? It's much more likely that we're going to have some unexpected 10% decrease in human welfare rather than a 10% increase in human welfare, and that's going to be really important. On the other hand, you might say that uncertainty might justify a wait and see approach. All right. So in finance, we've sort of developed this idea of option theory and real options, and this idea that if we don't know the full effect of our choices are today, then it might make sense to wait and see. Wait 5 years, wait 10 years, not wait forever, but wait 5 years, so there's better science about the effects of our choices, and make those choices then. Finally, I think the biggest critique and the biggest thing we should worry about for these analyses is the possibility of catastrophic events. All right, so I think that the term that Marty Weitzman, another potential Nobel Prize winner in environmental economics, is what he talks about is that is that the effects of climate change are vast and right skewed, in that even though the central estimates aren't so bad, right? The central estimates say that we're going to keep on chugging along pretty much like we currently are. There is some probability that catastrophic events could happen, the apocalypse could happen, that kind of thing, and we should address that. The problem that I guess my response to that is that the problem is we just don't know, right? The science is much better on estimating the central impacts, and it's much more weak estimating like these sort of tiny probabilities of, potentially really bad events, right? Just like just like there's some probability that there's going to be a huge catastrophic climate effect. There's also some probability that there's going to be some huge, I don't know, flu outbreak that kills off half the world population, or some asteroid that sort of blows up, that sort of totally cools the climate to another ice age, or that aliens attack. All right, I don't know. Pick any Hollywood disaster film. There's probably some probability that might happen. It doesn't mean that we should be worried about all of them. All right, but at the same time, it does mean that it sort of forces us to question whether these cost-benefit analysis based on sort of the average effect, not the worst-case effect, really tell us anything important. So the important thing to keep in mind as we think about the costs and benefits of dealing with climate change is that, there may be better uses of money. All right, that yes, there are these potential huge costs of dealing with climate change, huge costs that might come with climate change, but the costs of dealing with climate change and stopping climate change are also equally potentially huge. So using the numbers that provided by the United Nations Intergovernmental Panel for Climate Change, the IPCC, this is the body that won the Nobel Prize a few years ago. They basically suggested that we could curtail carbon dioxide emissions and stop climate change at the cost of basically reducing global GDP growth by 0.1%. And you think 0.1%, that's nothing, all right? But if you start adding that up, it's actually something substantial. For example, that 0.1% means an economy that's $3.5 trillion smaller in 2030. Now, again, we're talking about these big problems, but $3.5 trillion, that's real money. All right, 3.5 trillion to give that context is equal to half the size of the entire African economy. And so we're talking about enough money to sort of, basically double the income of half the people in Africa that we're going to spend to sort of curtail carbon dioxide emissions. All right. Also, slower economic growth means that there's going to be more people in poverty. All right. So, various macroeconomic estimates suggest that reducing growth by 0.1% means that there's going to be an extra 2.4 million people in poverty every year. More, slower growth, more poverty. That's a real consequence. And again, this amount of money, while it seems like it's only 0.1%, is still a lot more than what it would cost to say do things like reduce global poverty by half, reduce infant mortality by 2/3, increase access to water, sanitation, primary education. All these things that are much cheaper that we're not even doing. So why start with climate change when there's these other noble goals that potentially have more significant effects on the world? I think a big part of how I think about climate change comes from how the debate is framed. All right, people often talk about the cost of climate change, right? In terms of in terms of like animal species dying, and in terms of melting glaciers and things. But we also should think about the cost of stopping climate change. All right. Cost of stopping climate change means millions of more people in poverty every year. The cost of stopping climate change means millions of people, or lots more people that are going to die from cold. All right, the cost of stopping climate change means less money to spend on other priorities that we as a world civilization may think are equally, if not more important. All right. So how does this matter? All right, how does this affect how we should think about policies to stop climate change and policies that you could do in your everyday life to stop climate change? Well, to summarize this big literature in economics, basically what it largely finds and what economists largely agree on is that 1 ton of carbon dioxide emissions basically does $20 of damage to the world. All right. So in terms of how guilty you should feel from emitting 1 ton of carbon dioxide, that's basically $20 is the number you should be using. How can we use that? Well, you could sort of think about, the typical American generates around 20 tons of carbon dioxide per year, about half of that from electricity. So you could think, okay, well, my electricity, so that means my electricity use accounts for, say, about, 10 tons, and so 10 tons of carbon emissions at $20 a ton means my electricity use generates around $200 of environmental damage. All right, and if I want to think about, whether I should install a new air conditioner, whether I should sort of, get new light bulbs, you could think about, how much is that going to increase or decrease my electricity use, to think about what's the impact in terms of my damage to the world. Another thing to think about is pretty much how is driving gonna damage the world. So, if you go back to your high school chemistry, you could sort of calculate that since gasoline is basically mostly carbon, right? It's sort of these carbon chains that, with some hydrogen mixed in. And that basically when you burn carbon, it converts these long chains of carbon into basically carbon dioxide, right? You could just do some fancy math, sort of calculate that each gallon of gasoline, basically yields 20 pounds of carbon dioxide, all right? And 20 pounds is a convenient number because 20 pounds is basically equal to 1/1000th of a ton. All right, so every gallon of gasoline you burn is going to basically emit 1/1000th of a ton, or multiplying that by the $20 per ton, it's going to mean that each gallon of gasoline that you burn is going to do roughly 20 cents of climate damage. All right, so let's apply some of these numbers, all right, and sort of apply some of these ideas of using these numbers to the policy proposals we discussed earlier. All right, so just doing sort of this off the cuff, analysis using using $20 per ton, we get started thinking about whether all these ideas, the 7 ideas by Al Gore, these 5 other ideas, are good ideas or bad ideas. So I've sort of labeled the ones that don't seem to make much sense by this analysis, right? The red ones are the ones that don't make sense, green ones are the ones that do seem to make sense, and the black ones are sort of uncertain. The red, so basically banning coal power plants, it doesn't make sense to sort of have a general ban, right? What it makes sense is, it makes far more sense from an economic point of view, is to sort of do a cost-benefit analysis, by sort of, and we'll talk next lecture on how we force them to do that, on whether the emissions they're causing are, outweigh the cost savings we get from using coal, all right? And just the outright ban seems to be, the wrong approach. In terms of applying this to sort of, CAFE standards, fuel economy standards, it seems like actually that basically, I think the cost-benefit analysis said that it may be a good idea, but it makes certain presumptions about people being short-sighted, which may or may not make sense. Banning incandescent light bulbs, there are environmental savings from doing it, and people can save money from doing it. But I think the problem is that these cost-benefit analysis don't account for the intangible benefits of incandescent light bulbs, right? That basically, there's been a lot of heat from where there's been a lot of complaints because some people just don't like fluorescent light bulbs, and basically forcing people to sort of deal with that inconvenience for some infinitesimal cost savings is tiny. All right. How much electricity do light bulbs use? They use just a few percent of our electricity bills each year, which means that each person's incandescent light bulbs are only doing pennies of environmental damage each year. Those pennies will be eliminated if we sort of ban them, but whether that's worth the inconvenience is something else we should think about. Subsidized mortgages is a trickier one, especially with a given mortgage crisis, so I'll leave that out. Electricity grid changes. That's something we'll cover in a future lecture. Shifting taxes from a payroll tax to a carbon tax, that I'll cover in next lecture. I think economists love this idea, but may not happen. Capping carbon dioxide emissions immediately at current levels. Again, I think economists are going to say that a cap that doesn't account for the costs of things is basically wrong-headed. But basically, I think these numbers are going to be more helpful for thinking about things like, everyday things like whether or not you should use air conditioning or not. All right. So again, suppose your air conditioning bill accounts for, say, 10% of your electricity bill each year. We know that basically your electricity use is basically generating around, roughly $200 of environmental damage, which basically means that air conditioning is basically contributing to, say, roughly $20 of environmental damage each year. Again, would banning air conditioning reduce environmental damage by $20? Yes, but I don't know about you, but I really like my air conditioning, and I would much prefer to basically pay an extra $20 to help the environment in some other way than to basically sit in sweltering heat. All right. The same thing with bottled water. Bottled water, if you sort of calculate what's the environmental damage of bottled water, it basically comes mostly from the transportation of bottled water, which is a relatively small cost. All right. So again, if you note that the environmental damage from 1 gallon of gasoline is around 20 cents, but you could calculate that basically, you know, the environmental damage from transportation is, I don't know, maybe 5 to 10% of the cost of transporting that bottled water. So if you think that costs, I don't know, 5 to 10 cents to transport that bottled water to you, then the environmental damage of drinking bottled water and using bottled water is maybe another 1 or 2 cents. Now, again, yes, if we ban bottled water, would we reduce that environmental damage? Maybe. But at the same time, maybe it's worth that 1 or 2 cents of environmental damage to me because of the convenience that bottled water provides. The analysis for hybrid cars is a little more involved, but you could do the same thing and find that in general, people, you're not helping the environment in the most efficient way by buying a hybrid car. You could also sort of look at people think about local foods a lot, and people find that actually often people do more damage to the environment to eat local foods because eating local foods requires extra trips to the farmer's market, and driving your car a few extra miles to get to the farmer's market potentially it does a lot more damage to the environment than shipping that piece of broccoli from Mexico. One idea that seem to make a lot of sense is planting trees. All right, so I've been negative on basically reducing emissions in other ways, like air conditioning or bottled water, but then you might ask, what can you do? And so the question is, if you feel guilty about all the extra air conditioning you're doing and all the extra bottled waters you're buying, then you could sort of make up for all that by sort of planting trees instead, right? It would just cost $400 to plant 20 tons worth of trees, and that basically sort of totally eliminate all your emissions every year, and you don't have to feel guilty at all about anything you do. It's not that expensive, and as an economist, we want to encourage people to reduce emissions in the most efficient way possible. Sort of other policies that people think about to reduce carbon dioxide. This is a great photo I sort of took from Time magazine about these girls who basically spent a year trying to reduce their household carbon dioxide emissions, and look how happy they are. Look how proud they are, right? These are the pounds of emissions that they've reduced. But if you recall that basically, the value of reducing emissions is basically $20 per ton. All right, and so let's say that, this particular girl here who basically reduced her emissions by 440 pounds. That's a quarter of a ton. That's basically $5 of emissions from a year's worth of work. All right, this person here who basically did 1,000 pounds. That's $10 of emissions from a year's work. Now that's great. Maybe they had a good time and they learned a lot about the climate while doing so. But if all they wanted to do was reduce emissions and sort of help people in the best way possible, they could have probably each held a bake sale and probably done a lot more good for society than basically these numbers would sort of suggest. So this brings me to a peeve of mine, which is this idea that's been floating around in the New York Times and sort of various academics have pushed this idea that we should be planting, crops in cities, right? That we should be building skyscrapers in urban areas so that, we can reduce so that even people in cities can get to eat local food. And in some ways this drives me crazy, right? Because yes, we should be doing things to reduce emissions, but only things that makes cost-effective sense. And the idea that it could possibly make sense to use up land that could be devoted to say office space or residential space in urban areas instead of land in Iowa to plant crops just strikes me as crazy, right? You could go and look this up. An acre of farmland in Iowa costs about a few $1,000s. An acre of office space in Manhattan goes for roughly, I think, $500 million. And to think that you could possibly have enough, environmental savings, emission savings from just that 1 acre of crops to justify this, multi-billion-dollar purchase, just strikes me as crazy. All right. So, anyways, I'm sure I've said things that hopefully have helped you understand how economists think about climate change better. I'm sure there's probably things that you'd want to hear more about or things that you disagree with. I look forward to seeing your comments in the discussion board. For next time, the plan is to basically talk about, okay, so given that these are the costs of climate change, what kinds of policies should we enact to do something about it? All right, specifically, we'll talk about this, this question that comes up all the time, which is, cap and trade policies versus carbon tax policies. How do economists think about them? Hint, hint, economists prefer carbon taxes, even though the rest of the world seems to prefer cap and trade. But, we'll sort of give you the economic tools to start thinking about them in next lecture. I look forward to seeing you then.
Welcome back to the Udemy course on Energy and Environmental Economics. As always, this is Ben Ho, Assistant Professor of Economics from Vassar College. In the previous two lectures, we talked about the consequences of climate change, both the science and physical consequences of climate change, but also importantly, the economic consequences of climate change, which I think is largely misunderstood, both even by politicians, policymakers, and scientific pundits working in this area. Today we're going to turn to solutions, right? So we've talked about all the dire consequences or not so dire consequences, but the real question is, what are we going to do about climate change? And how do economists see are the best solutions toward dealing with climate policy? So historically, the way the environment's traditionally regulated in the United States and elsewhere has just been sort of the direct approach, or from the economist's point of view, sort of a naive approach, right? So if we see companies doing something we don't like polluting, then we just tell them to stop it, right? We pass a regulation, stop doing it, and that's that. A nice illustration of this is basically just to compare how sulfur dioxide, SO2 here, was regulated in 1972, and how it was regulated later under sort of more economically sensible policies under the Clean Air Act of 1990. All right, so what happened so the reason we care about sulfur dioxide regulation is this is one of the byproducts of burning coal. About half of the electricity in the United States comes from burning coal, and a lot of coal is dirty, right? And has sulfur particles. The sulfur particles get, is put in the atmosphere. They lead to acid rain and smog and other bad things. So we basically, we would like to sort of solve this acid rain smog problem to reduce the sulfur dioxide in the air. All right, so in 1972, they basically passed a law saying, all coal factories have to install what are called scrubbers, right? These are really expensive devices that they would install in the smokestacks that would literally just scrub the SO2 out of the air. All right, and that's great. The problem is that these scrubbers were super expensive, and the reason they were passed so easily is because, the companies didn't care that much. They were just going to pass on the cost to the ratepayers, to the consumers, and so the law was passed, and we have these really expensive, really inefficient scrubbers that are that were basically taking the sulfur out of the air, and it worked to some extent, but it was just costly, right? Because really, there's like three ways essentially to reduce sulfur dioxide. All right, the first is basically technology. That was the scrubber approach, but there's two others. One is basically we could just use less coal, right? It's possible that a cheaper way is to basically say, okay, well, instead of using coal, to produce electricity, maybe we'll use natural gas. Maybe we'll use less electricity overall. Another way to reduce sulfur dioxide is to switch to different kinds of fuel, right? Some coals are cleaner than other coals, and so instead of mandating this technology to be installed everywhere, even in places where it wasn't really needed, we could just encourage companies to like switch fuel usage. All right, so the real trick here is that the EPA sort of puts in one-size-fits-all solutions. All right, where what economics wants us to do is basically encourage firms to pick solutions that are the cheapest for their individual condition, and that was a policy put in place by the Clean Air Act of 1990, which essentially was a cap-and-trade system for sulfur dioxide. So I'll talk a little bit about these systems now, because cap-and-trade is a big part of how people today are talking about regulating carbon dioxide, and it's how carbon dioxide and other greenhouse gases are regulated currently in Europe. So here's a diagram of the cost of cutting emissions for two different firms. All right, and we're going to talk about different policies and how they lead to either efficient ways to cut emissions or inefficient ways. The way to read these diagrams is the one on the left. This is basically firm X. All right, and the one on the Y represents the cost for firm Y. All right, and basically over here, this basically represents cutting all emissions, and over here, this just represents cutting the first emission. So if firm X cuts all its emissions, it would be cutting this much. If it cut only one ton of emissions, it'd be over here. All right, and similarly, this is the first ton of firm Y, and this is the final ton of firm Y. And the cost is represented by this line, the marginal cost curve for firm X, and the marginal cost curve for firm Y. So it's relatively more expensive for firm X to cut emissions, right? The first ton is going to cost this much, the second ton this much, the third ton this much, and the final ton for firm X is going to be way up here, at some super high cost. Whereas for firm Y, it's relatively cheaper. All right, it's not always cheaper, so the last ton of emissions for firm Y is going to be up here at this level, which is more expensive than the first ton for firm X. But in general, all the way up and down the curve, it's going to be relatively cheaper for firm Y to be cutting their emissions. All right, hopefully that makes sense. Now let's look at how we could use this graph to sort of think about various policies for cutting emissions. So in a typical sort of command and control policy would basically just have the government come in and say, all firms, to be fair, must cut their emissions by, say, 25%. All right, so 25% roughly for firm X is over here. That's 25% of the cuts, and the total costs of their cuts would basically be, represented by this triangle here, right? The first ton costs this much, the second ton, third ton, fourth ton, and so on, so that the final ton costs this much for firm X. And 25% of the emissions for firm Y is roughly here. All right, so the first ton of emissions is down here, and the final ton of emission cuts for firm Y is over here. All right, and so this represents basically the total costs for cutting emissions between these two firms under a command and control system. The problem, though, with this system is that we're not really doing this in the most efficient way possible. All right, we're having firm X make cuts that are this costly, right, this high bar, whereas firm Y can make additional cuts that are that are down here at this sort of low, at sort of these lower bars. All right, so we're basically making all these really costly cuts over here when basically firm Y could actually do more at a lower cost. So there's basically some inefficiency going on. The way a perfect command and control system would work is that we would try making cuts at the lowest cost possible. All right, so the way we would actually do this is basically we would say, okay, well, who can make the cheapest cut first? Well, that would be firm Y, right? Because his marginal cost is lower, and then we keep having firm Y make it because it's cheaper for him until we get to a point here where basically the firm Y's cuts are more expensive than firm X's cuts. So then we'll come over here and make some cuts we'll have firm X make some cuts until it's more expensive for on the firm X side. So we'll switch. Right, and we'll keep on going back and forth, making cuts, telling the company that's most efficient, cheapest at making cuts, up until the point where we basically achieved exactly the same number of cuts as before, but just having sort of firm Y doing the majority of the cutting. Right, just because firm Y is better at it, they should be doing it. And we stop at the point where basically the marginal cost for cuts is going to be the same across both companies, right? Because if it was higher in one company, then it would be efficient to basically, allow the more costly company to pollute more and have the cuts come from the more efficient company. Of course, this requires a lot of knowledge from on the company's on the government's part, right? The government has to know exactly, the cost function of each company. The government needs to know, needs to be willing to basically sort of give these really precise, recommendations and regulations on a company by company wide basis. And realistically, this just could never happen, right? Government just not smart enough, and whenever they put such specific regulations on a per company basis, people are going to object. All right, but fortunately we have alternatives that sort of get us to the same point. The simplest alternative is just have a tax, right? To basically say that, okay, companies can pollute all they want, so long as you basically, but you have to pay a tax of T to do it, right? So this is this tax of T. Oops, didn't want to do that. This is the tax of T. Right, and so how does this work? Well, here a company is basically has to decide. Okay, should I make a cut or should I pay the tax? Well, so long as the cost of making the cuts is below the tax, he's gonna make the cuts, right? Up until the point where he gets to this point here. At this point, above this point here, he's gonna stop making cuts because it's cheaper for him to pay a tax on his emissions. So for the rest of his emissions, the company is just gonna pay this T in taxes to the government. All right. Similarly, for firm Y, so long as it's cheaper for him to make cuts, he's going to make cuts. Up until the point here where he gets to this point QY, where at this point it's more expensive for him to make the cut. So then for the rest of his costs, he's just going to pay a tax to the government. All right, and economists love this, right? It's basically simple. It's easy to understand. The government just sort of sets a tax, and and the firms respond to that tax, and we basically get to this optimal distribution of cuts, where basically firm Y makes his optimal amount here, firm X makes his optimal amount here, and the total costs of society are minimized. All right. So the problem with this, though, is that in Washington, tax is a dirty word. So people sort of turn to alternatives that work in a similar way, but not quite the same. So the preferred alternative to basically a tax is what's called cap and trade. This is basically what was implemented under the Clean Air Act in 1990, and this is basically what's used around the world to sort of regulate carbon dioxide, and it's probably the most likely candidate for policy in the United States. All right, and so how does this work? This basically says this works sort of like command and control, where we go to each firm and say, okay, you each have to make, say, a 25% cut to your emissions. All right, so for firm Y, that would be right here, and for firm X, that would say be right around here. All right, but then what we allow people to do is, instead of making those cuts themselves, we basically allow firm X and firm Y to pay the other other firm to make the cuts for them, right? So firm X is saying, oh, so I have to make this many cuts, but it's really costly for me to make these cuts. So instead of doing it myself, I'm gonna just sort of instead of making this particular cut myself, I'm gonna pay firm Y to make that cut for me. And this cut's really expensive too. The cost is way up here. So I'm going to pay firm Y to make that cut for me too. And we're going to keep on doing this to the point here where the cost of firm X doing it is exactly equal to the cost of firm Y doing it. All right, so that that again brings us to the point where basically the total costs are minimized, right? Where basically we have firm Y making this amount of total cuts, firm X making this amount of total costs, but firm X in some ways getting credit for for these other cuts here, but they're basically paying firm Y to make those cuts for them. All right, and some people say it's unfair. Some people say it's like paying paying someone else for your sins. But economists like this because basically we get to the point where we get the same amount of cuts for the lowest possible cost, and that's exactly why economists sort of like this cap and trade system. One final method for sort of also achieving the same amount of cuts is to basically auction off permits, right? So say we want a total amount of we want the companies to reduce their emissions by 25%. Well, we just say in order to emit, you basically need to buy you need to buy a permit from the government. All right, and what you would have is the same thing would happen. You would have an auction for permits. The equilibrium price for permits will be T, and basically you'll once again get this point where basically firm X is going to buy permits for so here firm X is going to buy permits for these amounts and basically make these cuts himself. Firm Y is going to make these cuts himself here again as well, exactly the same as before. And basically, buy permits for this amount of emissions. All right, so to sort of summarize all this, the main takeaway that economists have for sort of thinking about how policies to regulate emissions is that command and control is likely to lead to the least efficient outcomes. All right, just because it doesn't account for basically different companies having different costs or different companies having different methods to sort of achieve the same emission savings. All right, so market-based instruments, things like taxes, cap and trade, permit auctions, and to some lesser extent subsidies, should basically all work in sort of achieving should all work in sort of achieving the least cost method for achieving emissions. And the reason why we like having a lower cost method for achieving emissions is because lower costs, if the cheaper it is to reduce emissions, the more we can reduce for the same amount of cost of society, and that's a good thing. All right, so. One important caveat to all this, though, is that there's a difference between taxes and cap and trade and auctions, and that's basically, who pays for the money, right? So the total cost is going to be the same, but in the case of taxes, the government's going to get a lot of the money because, these companies are paying taxes to the government. It's the same case with auctions. People sort of like cap and trade more because here the government is not getting the benefit of the revenues. Instead, the money, the costs are the sort of the revenues from the emissions are sort of stay within the firms themselves. So they also achieve things at the lowest cost, but sort of the distribution of wealth is going to depend based on which instrument you sort of choose. All right, there's also another important caveat, which is that these three options are only the same, in the case where government sort of has perfect knowledge over sort of the costs and benefits of climate change, right? And in particular, sort of the cost that firms have for implementing these things. But a really important paper by Marty Weitzman in 1974 points out that if the government's not so sure about the cost of implementing solutions, then picking what either a tax or cap and trade could matter quite a lot. So Weitzman in 1974, in a paper that's part of a body of work that could likely win him a Nobel Prize someday, right? So this is Weitzman. He basically posed the question: what happens if we sort of get the cost functions wrong, right? So in our pretty pictures, it's really easy to sort of say that, oh, well, this is the cost of fixing things, and based on the cost of reducing emissions, and based on the benefits from reducing emissions, we can basically identify the optimal price of emissions, the optimal cost that firms should be paying per ton of emissions produced, and the optimal quantity of emissions, right? Here, so this is the marginal. So here we have the marginal cost curve, and here we have the marginal benefit curve, which is basically flat for some for sort of some technical reasons. And so, if we sort of look, so at the point where they intersect, this is the optimal price or tax for emissions, and this is the optimal quantity for emissions. And so the problem is that, what if we screw up? What if we sort of misestimate the cost of reducing emissions? What if the correct cost of reducing emissions is up here? All right. The problem with that is that under a tax system, that's fine. If it's really costly, if it's much more costly to reduce emissions, see this marginal cost curve is much higher than this marginal cost curve, then under a tax, that's fine. Basically firms are just gonna not gonna reduce emissions as much, but that's fine because they're going to do so at a point that's sort of still comparable to the marginal benefit curve. All right. On the other hand, if we sort of use a cap where we sort of tell firms what quantity of emissions to reduce, and the cost proves to be much higher than we anticipated, then that basically means that we're basically imposing a really high cost, right? So the vertical line represents, the height of this line represents the cost that firms are paying to reduce emissions, and we're forcing them to pay a much higher cost than the benefit of those emissions reductions, and therefore cap and trade is potentially highly, highly inefficient. All right, so to sort of summarize this big debate that happens a lot in the policy world, about whether a carbon tax is better or a cap and trade is better. In general, I think the main one that Weitzman pointed out is that it's easier to estimate the right price than it is to estimate the right quantity. All right, it's easier for us to know that that a ton of carbon is worth about $20, and much harder to know how many tons we should be reducing in any given year. It's just that's just a feature of how these things are estimated. The other benefits of carbon taxes is that it basically guarantees a price to the firm. Basically, it doesn't have the price volatility that cap and trade systems have. It produces more certainty for firms. It makes it harder for politicians to buy off constituents. All right, because basically, under a cap and trade system, the politicians help decide, how many credits people get, and they could often sort of redirect credits to basically campaign donors or their friends, and so a carbon tax takes out that sort of political rent seeking. And then also people like this idea that the money from a carbon tax can be recycled to lower inefficient taxes elsewhere, right? So economists sort of hate things like corporate taxes, and we hate things like savings taxes. And if we could sort of tax carbon instead, we could take that money and make and sort of reduce taxes elsewhere. All right. So but in the end, if economists sort of love carbon taxes so much, why is it that cap and trade is sort of so much more popular to politicians? Well, one is that people often say it's because under cap and trade, the government just sort of sets a quantity and the market decides the price. I mean, that's sort of true, but I don't buy this as a reason to support cap and trade. All right. The reason I don't buy this is because. The reason I don't buy this is because, yes, the market sort of decides the price, but the government can sort of easily affect the price by sort of, increasing the number of permits or reducing the number of permits. And so the market's really not deciding anything at all. It's still the government deciding everything. It is true that a real benefit is guaranteed reductions, right? But, guaranteed reductions at what cost is the question economists ask. And economists sort of say that, yeah, we want guaranteed reductions, but, we want to make those reductions at a pace set by the market. And basically, at a pace consistent with the costs of making those reductions. And so a carbon tax works better, at that. So we don't get guaranteed reductions in any given year, but we sort of get there at a sort of more consistent cost to society. The other benefit of a cap and trade system is that it doesn't sound like a tax. It actually is a tax, right? So if we make power companies pay, to buy permits to produce the electricity they produce, they're just going to pass on that cost to consumers. All right, and so consumers are going to wind up paying for these cuts in either regime. But if it doesn't sound like a tax, it's easier for politicians to make the sell. Also, maybe it is a benefit that politicians can buy off constituents, right? So a big reason why cap and trade was implemented in Europe versus a carbon tax. So Europe first tried passing a carbon tax, and it just didn't work, right? Because basically there are powerful companies that said, we don't like this idea. So when they implemented the cap and trade system, they said, okay, well, fine. In order for you to sort of convince you to support our plan, we're going to give our pet industries extra permits, right? Which is a little bit unfair, but at least it basically buys their cooperation and allows the whole bill to be passed in the end. And then one other benefit for cap and trade that a lot of people say is that, well, is that taxes are dangerous, right? So for economists, it would be nice to sort of say, oh, well, we'll take those taxes and use them to cut inefficient taxes elsewhere. But the cynics will say that, oh, whenever government gets extra tax money, they're just going to waste it on bridges to nowhere and sort of teapot museums. All right, so a cap and trade system sort of keeps that money from getting to government hands, and some people sort of like that feature of cap and trade. All right, so sort of but a couple of sort of big takeaways to think of I want to point out on this carbon tax versus cap and trade debate, which is that maybe a hybrid between the two might be optimal, right? So a hybrid between the two, where you basically have a cap and trade system plus some sort of guaranteed price of emissions, is might be a way to sort of have some of the political benefits of cap and trade, but still establish the price certainty that carbon taxes provide. Also, both at the end are going to be better than direct regulation. Like I said, command and control regulation is sort of ham-fisted and is going to lead to usually highly inefficient outcomes. And that sort of both work if you sort of allow government to sort of readjust it every year, which may or may not be feasible depending on sort of the government regimes. So to give you just some more history, again, I think the idea people sort of credit the pioneer of this idea was the Clean Air Act of 1990, which sort of set up a very successful sulfur dioxide trading, cap and trade market that very effectively cut sulfur dioxide emissions, right? When's the last time you heard somebody talk about acid rain in the United States? And also led to sort of rapidly declines in prices of emissions as technology improved. So people adopted a similar idea under the Kyoto Treaty between a number of developed countries that would basically create national caps on emissions, but would let individual countries sort of choose their method. Kyoto is basically expiring in 2013, and it's had a mixed success, mostly because I think people argue it allowed maybe too much flexibility for countries in how they decided to implement their carbon policies. I want to talk a little bit about the market for carbon offsets also, and this question earlier about, is it ethical to basically allow a company to pay another company to reduce their emissions for them? All right, and the typical way that this works is often through this market for carbon offset, where basically a coal company, is worried about its carbon dioxide emissions, and can pay, say, a landfill to burn its methane, right? So basically, so an example of a typical example of carbon offsets, one of the biggest examples is that landfills basically, landfills full of sort of organic waste start to decompose. It produces methane. Methane is a very potent natural greenhouse gas, and if we burn that methane, it basically reduces the potency of the natural gas. So if a coal company wants to sort of reduce their environmental damage that they're producing, they can basically pay landfills to burn the methane for them. Sort of another example of offsets that's quite popular is basically planting trees, right? So right now roughly 20% of the emissions in the world come from cutting trees down. Trees are quite a potent source of sort of regulating the amount of carbon dioxide in the atmosphere, and if we plant trees, that's basically going to sort of suck carbon dioxide from the air and turn that carbon dioxide into wood, right? So that's something that a lot of people point to as as being a good way to reduce emissions, but it's going to have a lot of pitfalls of carbon offsets, which I'll talk about in a second. And just as a sort of a silly joke, just like we could burn the methane that comes from, a landfill, people have talked about burning the methane that comes from cows. Probably not very practical, but it's something that people actually have looked into quite seriously. And so again, why do we care about carbon offsets? Why do we allow firms to do this? Well, because, in the EPA estimate for one recent climate bill, they found that allowing our offsets reduced the cost of compliance by 50%, right? Just like, in the diagram before, high cost cutters could basically pay someone to do it at a much lower cost. And if we cut the cost by 50%, that means we could actually, do a lot more for the environment for exactly the same cost as before. All right. And yet people are skeptical, right? People sort of call this, immoral. So some people call these carbon indulgences, thinking about the, medieval age practice of basically paying the church to absolve you of your sins. People point to Al Gore as being hypocritical. He spends a lot of money on carbon offsets because he lives in a really big house and he flies around the country, right? Just one transatlantic flight probably emits roughly about the same amount of carbon dioxide per person as the typical American does in an entire year. All right, so Al Gore flies around all the time, but he says it's okay that I fly around all the time because I pay for the carbon dioxide I'm emitting by planting trees and sort of through other carbon offset methods. As an economist, I think that makes perfect sense, but a lot of people don't. There's a nice website called Cheat Neutral that says that if you feel guilty about cheating on your wife, well, you could just pay some other husband not to cheat on their wife, and you could cheat on your wife all you want, right? So the net amount of cheating in the world is the same. And people sort of point to this to sort of talk about how laughable carbon offsets are. Again, as an economist, all I care about is the total amount of emissions in the world. I don't care about, cheating on someone's wife in particular. But, I just want to sort of reduce emissions at the lowest cost possible. But people sort of have issues. Also, carbon offsets in general sort of require careful scrutiny and regulation because it's possible to use them to cheat the system. All right, one of the concerns people have is permanence. What if I, get credit for planting some trees and a year later I chop those trees down and burn them, right? Totally negating all the efforts. So that would be an impermanent carbon offset. Another problem is additionality. If I was, say, going to plant a tree anyways, and I could basically sell someone the credit for planting the tree, but I didn't really do anything for the environment because I was gonna do that anyways, and it didn't really help. Leakage is a third problem with carbon offsets. This is what the problem that says that maybe I'll plant more trees, maybe I'll pay people not to cut their trees down in the United States. But by doing so, I basically increase the price of wood on the market, which encourages people to cut down rainforests in some other country, thereby negating all the effect they had, overall. So that's the problem of leakage. People talk about the co-benefits of carbon offsets, which is basically just maybe planting trees has other benefits aside from the carbon benefits. People talk about the difficulty of measuring how much carbon dioxide you get from, let's say, a single tree or from burning methane or from all these different methods. And people worry about the perverse incentives, right? That if I get to pay people, if I get paid companies to basically, cut their emissions for them, will that create incentive to basically create really dirty factories so that someone will pay me to to make future cuts? These are things that can be handled through smart regulation, and it's something that I've sort of worked on in my own research, but it's something that definitely needs to be addressed. And of course, one of the main concerns of all these regulations is, like I mentioned earlier, the distributional concerns, right? Who gets taxed? Who pays the tax? Again, the economists can make sure that we get the most efficient outcomes possible, but it's up to politicians to decide who pays for these cuts. Similarly for subsidies, who gets the subsidies, who pays for the subsidies. And it's not always who you think, right? We think, we should tax the big businesses, but taxing the big businesses will just lead the big businesses to pass on those costs to the consumers. And so it's important to be aware of just sort of, who's paying for this environmental cleanup. This is especially a big issue between countries right now, right? How much should rich countries pay? How much should developing countries pay? Actually, for rich countries, we're actually on a downward trend of emissions, right? At some point, big countries like the United States, we stop manufacturing things and we start focusing on services, and our emissions are start to go down over time. Whereas like sort of poor countries, rapidly developing countries like India and China that have lots of manufacturing increases coming up. they're going to have the biggest emissions going forward in the future. And so should we just, and their claim is that, well, we, in China should be allowed to emit more because you guys emitted more for the past 200 years. Now it's our turn. And if you want us to cut back, the rich countries should pay for it. Also, when we sort of think about implementing cap and trade questions, there's also issues of, international political economy, right? So it's relatively easier to think about instituting a policy for the United States where there's a federal government. It's sort of hard to think about doing that globally where there is no real international government that has any power. Other international concerns is the effect of climate change on geopolitical conflicts, right? So one reason why we should be worried about climate change is that, higher temperature leads to more famine, which leads to more war. We also should be worried about relocation and the cost of relocation, as low-lying countries like Bangladesh are going to face large amounts of flooding, and think about how do national identities get redefined when countries start flooding underwater and people and there's mass migrations, and then the distributional concerns that we talked about before. Right? And the reason why this matters, so a very practical reason why this matters is basically we don't want to just export emissions, right? So basically putting a carbon regulation in the United States, so the biggest example of this, it might just cause emitting firms to move to other countries. Cement is a relatively big emitter of carbon dioxide. And so a lot of models say that if the United States decides to regulate carbon dioxide within the United States, all the cement producers will just move overseas to, say, Mexico or Spain or China, for example. And so we actually wouldn't reduce any of the world emissions at all. We just would just sort of shift them to other countries. People say, okay, we could fix this by sort of putting tariffs on imported cement from other countries to make sure that they account for their carbon emissions, but that that's going to interact with sort of treaty obligations for free trade put in by the WTO. All right, so these are just tricky concerns, and the tricky concerns are basically if every country, even if we get every country to sort of implement, their own cap and trade system, how we might merge these different systems is also something that is also a question of ongoing debate. All right, so in this lecture, we've basically pretty much covered just some of the main debates within economics as to how climate policy should be implemented. Again, thank you for bearing with me as I sort of cover some of these more abstract technical details. On the next lecture, I'm going to return to the more concrete questions, all right, and basically explore some of the technologies of how we might sort of reduce emissions, right? So this lecture was more about sort of the abstract economic policies. Next lecture will return to asking questions like, what role will solar panels play? What role will methane play? What natural gas, clean coal, all these different technologies for basically for addressing the problem of climate change for the upcoming future. Thanks a lot. Welcome to the last lecture in Udemy's series on energy and environmental economics. As always, this is Ben Ho, economics professor at Vassar College. And even though this is the last of a series, each lecture is sort of designed to stand alone. And in this lecture, we'll be talking about the technological solutions dealing with climate change. So before getting started, I want to make one thing very, very clear, and that is economists don't believe in picking winners. All right. So even though this lecture will mostly be talking about the different technologies that could go into fixing climate change, ranging from solar panels to algae-based fuels to geoengineering, as economists, we sort of think that policymakers and policy wonks and academics don't have the right foresight to sort of figure out what technology is going to happen next, right? Economists sort of believe in fixing markets instead, which is why the previous lecture was all about, economic policy. How do we fix markets to make sure all the proper costs are internalized so that markets will sort of choose the best technology themselves? Because as we'll talk about, when government tries to pick technology and pick winners, it tends to get into trouble. All right, but then again, I know a lot of you out there are probably people in the market, are market participants, and you need to know what are the options out there, what technologies exist. And so, my job here is to help inform you so that you have a better idea, but I don't want to sort of advocate one technology versus another. That's for the market to decide.
So as we start thinking about the technologies that will help address climate change, it's helpful to sort of think about where do emissions come from. All right, so the chart on the left here basically is a chart of U.S. emissions over the past 20 years. You'll see that basically within the U.S., almost all emissions comes from energy. All right, the other thing you'll notice from this chart is that emissions have been increasing steadily, but over the past few years actually started to decline, partly due to the recession, but partly because of changes in technology. Right, we're not a manufacturing-based economy anymore. We're more of a service-based economy. Most of our production comes from services, things like nursing and dancing and cooking and waiting, and all these things actually use less energy than they did before. So actually, our sort of our emissions are sort of leveling off. The other thing, though, is that, yeah, most of it's from energy, but a little bit is from agriculture, a little bit is from industrial processes and waste, but energy is the main part of it. And also down here, we actually have negative emissions from land use and forestry. All right, what this basically means is that over the past 20 years, we're actually planting more trees than we're cutting down, and so that trees are basically a net reduction in our emissions because we're planting so many trees. People often, don't appreciate that about the environment, but actually some things are actually getting better, and one thing is the U.S. is getting more and more forests each and every year. All right. Sort of, if we want to break things down a different way, on the right-hand side, we basically, look at the sectors that sort of generate greenhouse gas emissions. We find that a big chunk of it is transportation, and when I say transportation, I basically mean cars and airplanes, and all that comes from all those emissions come from burning oil. And then the biggest chunk though is electricity. And so pretty much when we're talking about reducing emissions within the U.S., we'll be talking about these two sectors. Though that's a very U.S.-centered point of view. If we look globally, the story is a little bit different. So whereas in the U.S., you see that basically emissions are sort of pretty flat, and these are projected emissions up until 2030. U.S. emissions are sort of relatively flat over the next 30 years. Global emissions are going to be huge. All right, and a big growth in global emissions is basically going to be from China, which is basically growing, growing exponentially, and so basically their emissions are going to be growing more and more. So whenever we think about climate solutions, we have to think about these things from a global perspective, because it's basically the developing world where most of the emissions growth is going to come from. It's also worth noting that on the right-hand side, the composition of emissions from worldwide is different than within the U.S. Whereas in the U.S., where most of our emissions come from energy and transportation, a large chunk of global emissions comes from land use and forestry, as forests are being cut down, and agriculture, and so we should and a relatively small chunk from things like transportation. And so we should be aware, as we think about attacking this from a global problem, that basically thinking about the forestry and agriculture are going to become very important components as well. The rest of this talk will basically focus on 4 categories of solutions to climate change. All right, the categories are basically going to be electricity is one. All right, that's the biggest chunk of U.S. emissions. Oil and transportation is going to be the second one. The third one is basically going to be agriculture, which again is minimal in the U.S. but really important globally. And the fourth one is basically this idea of geoengineering, which is basically grand technologies to basically change Earth's atmosphere by, say, blocking out the sun or such other grand Mr. Burnsian style solutions to climate change. We're going to start off with electricity. So this is a fascinating picture. It's a diagram put out every few years by the Lawrence Livermore National Laboratories. I invite you all to sort of pause the video at this point and just stare at this for a little bit. On the left-hand side is all the sources that the United States gets energy from, ranging from solar, nuclear, wind, geothermal, gas, coal, petroleum, etc. And basically these lines sort of trace out where the energy goes. All right, so basically these sources up here, they all sort of go up to electricity generation. All right, and what we see down here is oil. Oil pretty much all goes toward transportation. All right, a little bit toward industrial use, but most oil goes toward transportation. And we notice that all these fuels that people talk about that go toward electricity, like solar power, wind power, none of it goes to transportation really, because on the whole, cars run on oil, right? There are very, very few cars out there that run electricity. The few that are out there get a lot of press, but they make up a tiny fraction of 1% of cars on the road. So for the near future, cars and definitely all planes, pretty much all run on oil, and so all the oil energy is going toward vehicles. All these diverse fuels are going to electricity, and then basically this is how, and then these 4 sort of say what sectors use different kinds of energy.
Another thing that's sort of pointed out is that actually a vast amount of energy is due to waste. All right, so basically, of all the energy produced in the U.S., basically, this is the stuff that's actually used, and this is the stuff that's sort of wasted in terms of heat. And basically, that this also points to another potential source of energy, which is basically conservation or making the energy products we use more efficient. Right, more fuel efficient cars, more efficient appliances. That's a way to sort of capture all this wasted energy on the right hand side of the graph. Alright, so let's turn our attention just to electricity at first, and we're going to talk about all of the different ways that the US at least generates electricity. We're going to start with coal here, and the number here, 40%, represents about the ratio of electricity in the United States that comes from coal, and this term LCOE stands for levelized cost of electricity, and that pretty much just tells you, how much per kilowatt hour does it cost to generate this coal. And an MIT study finds that for coal, it's around 4 to 5 cents. If you open up your electricity bill, you'll see that you probably pay between 10 and 20 cents per kilowatt hour for your electricity. So the 4 to 5 cents goes to paying for the coal, and the rest goes for transportation, administrative, and other such fees. All right, and the thing, one key thing about coal is it's the dirtiest way we have to to produce electricity. It doesn't create as much soot and sort of nitrous oxides and sulfur oxides as it used to. Those were sort of the main causes of acid rain. We sort of cleaned that up through regulation, but it still produces a lot of carbon dioxide, sort of twice as much carbon dioxide as natural gas, and just 100% more than basically solar or nuclear that really hardly produces any carbon dioxide at all. All right, so it's dirty, but it's also the cheapest way of producing electricity, and there's tons and tons of it. If you sort of look at the coal resources in the United States, if sort of this sort of circle represents all the coal and oil resources we have in the U.S., coal is a big chunk of it, and this tiny circle represents basically how much energy was used in terms of oil use in the United States in 1 year. All right, so we have tons and tons of coal available. It's just the trick is getting it out of the ground in a clean way, and that's sort of the tricky thing. All right, so for now, the idea is that maybe we're going to clean it up, and there's going to be ways to we can sort of suck the sulfur out of it and suck the soot out of it, but there's no good way to sort of suck the carbon dioxide out of it just because there's so much. There are some technologies to basically take it and sort of bury it underground, but it's really expensive. And sort of the Obama EPA recently has basically banned all new plants until they've sort of perfected that technology. So natural gas is probably the next biggest source of energy, electricity production in the United States, accounting for about 1/5 of the electricity we use. It has a levelized cost of electricity about 3 to 9 cents per kilowatt hour. 3 to 9 cents, primarily because the price of natural gas varies a whole lot. All right, so if you look at these gas prices over the past 30 years, you see it goes from like as low as 2 cents all the way to as high as 12 cents, and just in the past 10 years, it's been sort of spiking up and down from 10 to 12 to down to 2. And that basically is led to very, sort of erratic prices. Part of the reason for sort of these spikes up and down is because it sort of, follows the price of oil. But a big part is because in the past 10 years, this new technology called hydraulic fracturing, where you basically sort of pump water deep into the ground, like 2 miles underground, that to release extra natural gas, has made natural gas production really cheap in the United States and soon in the rest of the world. So people are sort of predicting sort of an age of cheap natural gas going forward, and this has lots of important implications. All right, so first of all, right now cars are all run on oil, but maybe in the future they'll be run on natural gas. Already a lot of buses and trucks are converted to run on natural gas. It's still dirty, but it's still cleaner than coal. All right, so basically we can produce the same amount of electricity from natural gas compared to coal. The emissions are basically half as much. The gas itself is actually really bad for greenhouse gases and global warming, but methane at least has a relatively short half-life of about, say, 10 to 20 years, and so we're not too worried about the methane in the atmosphere as we're worried about the carbon dioxide, so that's actually okay. It's sort of nice that actually now that people are aware that there's all this natural gas, there's no more absurd calls for peak oil apocalypse. You see all these sort of TV shows based on this idea that we're going to all run out of oil. So I think no one's really worried about that. There's plenty of fossil fuel resources out there. The trick is how do we extract them all in sort of a clean way.
And one final issue with natural gas that's sort of changing is that it's historically been difficult to ship and to trade. That's changing now as we sort of are building, gas liquefaction plants that allow us to sort of ship them long distances without pipes. But that's something else important going forward. The next biggest source of electricity generation in the United States is nuclear power, accounting also for about 1/5 of the electricity produced in the United States. Is the levelized cost of electricity of around 5 to 8 cents, according to those MIT studies. And so it's somewhat more than coal and somewhat more than natural gas when the gas prices are low, but cheaper than actually most renewable sources. And the best part is that it's relatively clean, right? Except for dealing with the nuclear waste, which is a hassle. There's almost no carbon dioxide emissions, and so in terms of doing something for global warming, if the world ran only on nuclear power, we'd be in really great shape. But that's unlikely to happen anytime soon, primarily because of one word, Fukushima. Right, that was sort of the nuclear disaster in Japan, and even though no one died after the Fukushima disaster, at least from directly caused from it, while thousands of people die each year from coal mining, it's still just the public perception of nuclear power is totally shifted to the point where they've sort of decided to sort of abandon nuclear power in Germany and large parts of Europe. And it's unclear, whether it will go forward at all in the United States. Even before Fukushima, nuclear power in the United States has not really been expanding too much. They've had huge permitting issues, huge insurance issues against disaster. There hasn't been any new siting in decades, primarily because nobody wants a nuclear power plant in their backyard. So it's unlikely to see growth going forward. But in some ways, you never know, because if we decide that we really want to, address global warming, nuclear power may be a great way to do it. Past decade, probably the most talked about renewable source of electricity is wind. All right, and if you sort of look at this chart of sort of wind power capacity, it was tiny 30 years ago, and just sort of in the past 10 years, it really started to sort of take off. Even though it's really been taking off, it's really only accounts for about 1 to 2% of the electricity produced in the United States, and it is growing fast, but it's sort of leveling off, so it's not clear just how much further this can go. It has a levelized cost of electricity of 5 to 6 cents, so more than the fossil fuels, but not a whole lot more. But it has a lot of problems, all right? So first of all, it's intermittent, and so, it only generates power when the wind is blowing, and so it's going to require basically new transmission lines to get, from where the wind's blowing to where we need the power, and basically new storage facilities like big batteries. So we can store power on a small scale, but large-scale battery storage is basically just too expensive right now. It's pretty close to cost-effective, though. So like I said, coal is 4 to 5 cents, natural gas is around the same, wind is just a little bit more, but at the moment, in order for it to be effective, it basically depends on sort of substantial government subsidies of around 1 to 2 cents per kilowatt hour, or about 20 to 30% of the production value, and also sort of state RPS regulations, which basically mandate that a certain amount of electricity has to come from renewable sources. Finally, perhaps the most talked about renewable electricity source, the one that people think about when thinking about renewable electricity first, is often solar electricity. All right, which has the potential for being a game changer. So right now, really, it's very tiny, right? It accounts for less than 1% of electricity in the United States, and the reason for that is because it's super expensive, right? It has a levelized cost of electricity of say 5 up to 30 cents per kilowatt hour. So it's just very costly. But basically, people sort of expect the cost will plummet, right? So these are sort of the past costs of solar electricity and predictions going forward. And the technology really has advanced by leaps and bounds over the past 10 years, both in terms of sort of thin films, but also thinking about doing both solar panel at the household level, and also at the utility level. It's still expensive though, right? And I think the recent Solyndra disaster, where basically the Obama Department of Energy decided to give a loan guarantee to Solyndra, which is a solar panel company in the United States, basically cost the government $500 billion when Solyndra went bankrupt. So, to give you a context, the Manhattan Project in today's dollars is only $4 billion, and $500 million, or a good chunk of that, basically just, poofed and disappeared because this company just couldn't compete. All right, and they sort of say that the reason they couldn't compete is because of foreign subsidies, and in some ways that's true, but in some ways it's just it's hard to compete in these manufacturing industries. And in some ways, these foreign subsidies are good because they basically are producing cheaper solar power. And the reason why we are moving so fast on the curve is because other governments are investing so much money of their own money to make it cheaper for the rest of the world to produce solar. So economists on the whole think that the U.S. should be happy that the foreign countries are subsidizing their companies, because it helps us in the long run. I just sort of touched on, just a handful of the renewables, the ones that are most common and the most common sources of electricity. But there's lots of other possibilities out there, right? So sort of being at the White House, you sort of hear all sorts of kooky ideas of people coming in, and some of them might be quite viable. You never really know. So geothermal probably is the most viable of these other ones, but people have also sort of are making power from algae. People suggested of sort of tapping electricity from the aurora borealis. People sort of, suggested tapping electricity from hurricanes. So the craziest idea here is basically collecting the gas that cows produce and burning it. The future may never know. And as I said at the beginning, economists again don't believe in picking technologies. They think that governments get in trouble whenever we try, but and so the best thing to do is to sort of let market participants, figure it out for themselves, and let the market decide once we get the incentives correct. So I think just to sort of summarize electricity, the main thing I want to say is the future is unpredictable. So in the 70s, people talked about solar panels. In the 80s, people talked about hydrogen fuel cells. The 90s, it was all about natural gas. In the recent years, it's all about natural gas. And maybe it's going to be solar again. We don't really know. The future remains, open to see. So moving on to transportation. In the United States especially, transportation is one of the major sources of greenhouse gases, accounted for about a third of U.S. emissions. It's not as big a deal in the rest of the world because the rest of the world doesn't have cars or airplanes yet, at least not regularly, but that's going to change in the very near future, so it's something we should all be aware of. One of the most notable things about transportation is that if you think about it, almost all our transportation needs, especially in the U.S., come from oil, right? So whereas electricity, we get electricity from coal and solar and wind and all these other sources. For driving around, it's all oil. Gasoline, diesel, jet fuel. All these things all come from the same petroleum, and that's sort of what causes a lot of the problems we have in the oil markets. One thing that sort of people talk about a lot with oil is people sort of worry about it running out. All right, which I think is sort of a crazy idea. We talked about that in an earlier lecture, but it's also a crazy idea because there's so many alternatives to oil out there that are available. They've just been expensive, but it's not like we're going to run out. All right, so this is a table that we made at the White House back in 2006 about how expensive does oil have to be for these other alternatives to sort of come online? And basically what you find is that, once you get to $50, $60, $70, all these other alternatives to oil become really cost effective. And, there are ways to produce oil without using the traditional petroleum. All right, and today with oil prices hanging around $100, all these are coming online. So, for example, oil sands and converting coal to liquids, oil shale, these are all things these are all technologies being done today. The problem is they're all really dirty, all right? They tend to basically produce twice as much emissions to produce this oil as regular oil. And so, oil is already a relatively dirty fuel, and basically these emissions make them more so. So that's sort of a bad thing. Ethanol is a reasonable one, and we'll talk more about that on the next slide. But it too has its controversies. Another possibility is to somehow sort of capture the excess carbon dioxide from these other oil producing technologies. But as I said, like in electricity, it's really hard to capture carbon dioxide and bury it underground. We just don't have the technology for that quite yet. Probably the most viable alternative to oil in the near run is basically biofuels, all right? Or basically generating gasoline and sort of, gasoline-like products from biomaterial. You may not have noticed, but already roughly about 10% of the U.S. gasoline supply comes from corn. We're roughly about 1/5 of our, corn crop goes to making ethanol. And this is and so you can see that the trends over the past sort of 10 years has been growing, mostly due to government regulation.
All right. The problem is that there's lots of ways to produce ethanol, and corn is actually one of the least efficient ways. The reason we do it here in the United States so much is because, well, the U.S. has lots of corn. Sugar is actually sort of more efficient, and the problem is that most of the sugar that's good for producing ethanol comes from Brazil. So we're not thrilled about importing from Brazil, even though economists all think it's perfectly legitimate. Sort of the holy grail of sort of ethanol is this idea of producing ethanol from cellulose, which is sort of corn waste or just sort of the waste products of plants. Right, so traditionally we produce the corn the way we've always done. We take the grains, ferment it sort of like vodka. It's alcohol now. That's basically ethanol. But cellulose is basically taking the stalks and either burning the stalks to produce energy or using enzymes to sort of convert those stalks into energy. The technology is there, but it's really, really expensive, and so we've been waiting for a breakthrough to make it cheap. It hasn't quite come yet. A final possibility is algae. That too was really expensive, just to collect enough algae in one place to basically produce large quantities of ethanol. So all this remains to be seen. People often worry about the energy content of these different fuels, but sort of most studies published in the Proceedings of the National Academies of Science sort of say that they're all actually pretty good in terms of energy content. Corn is the worst, but it's still better than oil, and cellulosic and algae-based ethanol is probably the best. People often also worry about the effect of ethanol and corn on food prices. Because we are using such vast amounts of corn on gasoline, people think that that's driving up food prices. Actually, if you look at if you look at it economically, you find that it does have some effect on corn prices and food prices, but it's really small, right? Most of the increase in food prices has been due to basically droughts or basically increased demand from India and China, and so that's actually not a big worry too. People worry about the environmental impact of these things. So yes, they produce less greenhouse gas emissions than oil, but requires farming a lot of land, which requires sort of more water, and all these other things. I think most economic studies sort of find that these impacts are relatively small compared to the benefits you get from sort of switching from oil, but it's something else we have to worry about. And then the final thing to worry about for biofuels is this compatibility question. Some people worry that ethanol is more corrosive than gasoline, and it will corrode like gas tanks and will corrode pipes. But in general, I think most experts believe that this is relatively easy to fix with new technologies that are relatively inexpensive. Probably the most exciting new development for transportation, though, is electric cars. Right now, there's been a lot of talk about electric cars, whether the Tesla Motors, the Chevy Volt, or the Nissan Leaf, for example, but no one's really buying them, right? So even the much hyped, hybrids like the Prius, you see them all the time on TV. You hear people talk about them, but they really make up, less than 1% of car sales, all hybrids put together, and electric cars make up a tinier fraction of all that. So when I say electric cars, I don't mean the hybrid cars. The hybrid cars pretty much still run on gasoline. They just use an electric battery to make the gasoline motor more efficient. What an electric car is a car that basically runs off the electric grid, right? You plug it in somewhere, it charges your battery, and you go from there. So this still raises the problem of basically how is that electricity produced. But in general, most studies say that because electric motors are much more efficient than gasoline motors, that even basically getting electricity from coal power, powering your car from a coal-powered power plant is likely better than gasoline. And if we power your car from a natural gas plant or from a wind plant, it's much, much better than gasoline. All right, so I think this may well be the future in terms of how we power cars. I think they're very efficient, and that they allow us to get energy from a lot more different fuel sources. But it takes a long time for cars to turn over, right? So cars turn over about every 15 years in the United States because, if you buy a new car in the United States, it's used for roughly 15 years. And actually globally, the cars last another 15 years after that, right? So pretty much if you buy a new car here, someone's going to be driving it 30 years from now, which pretty much means that even if everybody started buying all electric cars today, it would take 30 years before the whole world was converted. And that's not going to happen, right? So this is something that we're talking about decades, if not a century, before the entire car fleet changes over. So it's something we should anticipate and look forward to, but it's something that will take place over a long, slow period of time. All right, so just to summarize, in terms of transportation, most fuel comes from oil, but a growing number of fuel today is coming from biomass like corn and sugar, but that has its own environmental problems. Most likely, the future is going to be electric cars, but again, that'll take a long, long time before the global car fleet shifts over. All right, now I want to turn to agriculture. Agriculture is pretty much relatively a small part of U.S. emissions, but a relatively larger part of global emissions. So it's something important to think about as we think about the global problem of climate change. So one thing to note is that global deforestation actually counts for 1/6 of emissions every year, right? So if we found some way to get people to stop cutting trees down, that would just sort of cut our emissions by 1/6, which is quite a whole lot more. And then if you think about it, and if instead of just cutting trees down, we could actually start planting trees, then we could actually start bringing bring global emissions even more below that. All right. So in the U.S., we're actually planting more trees and cutting down each year, which basically means that trees in the U.S. are sucking carbon dioxide out of the atmosphere for us. And we could think about doing that on a larger scale, right? So basically, right now, if you want to, you could go to a carbon offset firm and pay someone to buy you a tree. Or, so Freeman Dyson, the physicist, pointed out that, if we really want to, we could take out all excess carbon in the atmosphere by planting 1 trillion trees. 1 trillion trees, yeah, that sounds like a whole lot, but if you think about it, that's 6 billion, there's 6 billion people in the world, right? If every person just plants 1 tree a day, for a few years, then we'll have 1 trillion trees. So this is not a, likely solution, right? But I think it puts into context how powerful trees could be if we just sort of, if we decide that this is the way we want to go about tackling climate change. Or alternatively, just agricultural practices themselves account for 1/8 of global emissions. And there's a lot of research recently to say how changes in agricultural practices, like no-till agriculture or managing manure better, could substantially reduce emissions. So little things like this. So when we think about reducing emissions, it's helpful not to think just about the flashy technological stuff like solar panels, but also just about what we do with our cow manure. The final sort of subcategory I want to talk about for solutions to climate change is sort of geoengineering, which is sort of this crazy science fiction idea. All right, this idea is like somehow coming up with some technological magic bullet to take the carbon dioxide out of the air or to stop warming. Some ideas are basically to make clouds in the sky to block out the sun like volcanoes do. All right, we basically put soot in the air, and that's going to that's going to darken the sky, and it's going to cool the world down. Another thought is basically to seed the ocean to encourage algae growth to suck the carbon dioxide out of the air. Richard Branson, head of the Virgin conglomerate, has offered a contest for anyone who could do this. One idea is to make these giant carbon dioxide scrubbers that would just suck carbon dioxide out of the atmosphere. Most of these ideas sound crazy, and they probably are actually crazy, but at the same time, they're potentially much, much cheaper, right? Even if it costs $1 billion to produce one of these, giant devices to clean the air, that's still a tiny fraction of the cost of sort of converting all the cars in the world to electric cars, or basically converting all the power plants in the world to solar, right? Those changes cost trillions, whereas we might have some crazy technology that costs billions that might save the day. All right, so just to sort of wrap things up and conclude, in terms of sort of summarizing climate solutions, we talked about 4 main categories of solutions to climate change, ranging from electricity to oil to agriculture and to geoengineering. One thing I want to point out is that there's all these different technologies, and these different technologies all have different costs, right? So when we want to evaluate, whether an idea is a good idea or a bad idea, it's helpful to think not just is it it's helpful to think how expensive will it cost to use. All right, and so this is a nice chart that basically sort of shows the different costs of different ways to cut carbon dioxide from the air. Some are relatively cheap, like basically like insulation and fuel efficiency improvements could actually have negative costs. Things like nuclear power and cellulosic ethanol could have relatively small costs. Massive forestation has relatively higher costs. And sort of getting rid of coal actually has some of the highest costs out there. And so it's important to think about when we look for solutions, we should focus on solutions down here that basically have the most emission reductions at the lowest cost. All right, and so I think that's sort of the summary for this lecture, but that's also sort of the summary for the course. Basically, one thing, I think the central idea of economics is pretty much that policies should be cost effective. All right, we should basically choose policies that maximize benefits while minimizing costs, and not just do what sounds good. We should sort of think about policy, and all of economics is based on identifying these policies, and hopefully, this course has helped you sort of, identify them for yourself. Important to this cost effectiveness analysis is that magnitudes matter, right? So people could say, oh, solar panel's so great because it doesn't emit anything, but it's important to know, how expensive is it? How much carbon dioxide does it save? All these measurement numbers are really important when thinking about what policies are good or what policies are bad. And the final thing is that incentives matter. All right, that basically economists are all about getting the incentives right, not picking the right technologies. I've talked a lot about technology today, but I don't want to sort of get into anyone's head that I know what technology is the right one. I don't think anyone really knows that. That's for the market to decide. But it's important to sort of think about getting the incentives right so that the market picks things properly. And that's one of the core messages in all of economics that I hope to get across. Anyways, thank you so much for bearing with me. I really enjoyed teaching this class. Feel free to keep on sending questions. I'm always happy to answer them. This is sort of the last course of the main series of lectures. If there's sort of demand for it in the future, there's a few bonus topics that I teach sometimes in my regular class. Basically sort of thinking about how behavioral economics, my field of research, comes into play. Thinking about the politics of climate change and sort of talking about non-market political analysis and talking about my experiences at the White House. Thinking about sort of the impact of climate change in agriculture, which has a big effect. So, if people are sort of especially curious on any of these topics, feel free to let me know. In any case, again, thank you very much, and hope you had a good time. Bye.
Hi, and welcome to Lecture 3 of Udemy's course on Energy and Environmental Economics. As before, this is Ben Ho, Assistant Professor of Economics at Vassar College. In the last lecture, I tried to convince you that cost-benefit analysis is probably, a reasonable way to sort of evaluate, how you should take decisions, how society should make decisions. But especially in the context of the environment, there are a lot of sort of practical questions as to how we actually implement cost-benefit analysis that I hope to address today. I think one of the main reasons people object to using cost-benefit analysis to understanding environmental problems is precisely because the benefits are often so difficult to measure and so difficult to quantify. But yet, economists have spent decades trying to perfect their techniques, and I think we've come pretty close to coming up with convincing ways to sort of measure these environmental benefits. All right, we divide these benefits into two categories. The first is the tangible or use value of preserving the environment. These are the sort of the practical everyday uses of, say, discovering new medicines in the rainforest or preserving our parks to visit for recreation. The second is basically the intangible or non-use values of preserving the environment. These are just the idea of having a pristine Arctic National Wildlife Refuge, or preserving endangered species from being extinct. These are trickier to measure, but we have our techniques, and I'll discuss them, in the upcoming slides. Along the way, we have sort of three tricky questions that that come about when sort of measuring the benefits of the environment that I'll sort of talk about in length. One is how do we measure the value of life, the value of human life especially, but even the value of animal lives. The second is how do we measure the value of $1 to different people, right? So different people of different income levels or may experience the value of money differently. How can we accommodate that, especially when we're worried about inequality? And the third tricky question is how do we deal with uncertainty? Economists have a lot of tools of dealing with uncertainty, but especially when it comes to the tremendous amount of uncertainty with environmental outcomes, that's something that we'll definitely have to address when measuring environmental benefits. Take a second and ponder for a second how you would measure the use value of a few environmental goods people think about quite often. For example, what is the use value of a national park? Or how would you go about quantifying the use value of reducing factory emissions? What about the use value of cleaning up a toxic waste site? How about the use value of potential future medicine found in the Amazon rainforest? Or finally, what is the use value of having a night sky? All right, these are all sort of tricky questions, and economists actually have developed tools to sort of address each of these. For example, the use value of a national park might be easiest, but I think economists tend to think that people are willing to pay what they value for something.
All right, so if you value a candy bar at $2, then by paying $2 for the candy bar, you demonstrate that that's what you value the candy bar at. Similarly, for a national park, if we sort of had a entrance fee at a national park, and people are willing to pay that entrance fee, that gives us some measure of how much people are willing to pay to keep that national park alive, and the value that the national park creates for them. All right, that's the use value part. Another way that people sort of value national parks, especially ones that are free, is to see how much effort are people willing to put in to get to the national park, right? To say that if you're willing to put in, 5 hours of driving, plus gasoline, plus hotel stays, just for the ability to visit the national park, we can sort of add up all those numbers and say, oh, well, maybe the value of the national park is, the value of the effort that you took to actually use it. What about the value of reducing factory emissions? So there's a couple of things here we could do. One is basically, so say the factory is polluting some, smelly gas that makes it unpleasant to live in. So what we could do is we can compare two houses, one by a clean factory and one by a dirty factory, and compare the difference in prices, right? So say the house by the clean factory is $20,000 and the one by the dirty factory is $10,000, then we could sort of infer from that the value of cleaning that factory up is going to be $10,000 of savings, and that's how much value we create by that's the benefit we create by cleaning that factory up. All right, we could do a similar approach to thinking about cleaning up a toxic waste site by comparing the change in local property values before that, with and without that waste site. We could also sort of add up the health consequences of having the toxic waste site there, or similarly the health consequences of having those factory emissions, right? And you could sort of add up. Okay, well, these emissions lead to an additional 3 cases of asthma each year in this town. We could go and sort of value how much do people spend to sort of avoid that asthma, or how much do people value their life with and without asthma, which we'll talk about a little bit when we talk about the value of life, and use that to sort of measure the use value of cleaning up emissions or cleaning up toxic waste. Down here, these are, here are two possible environmental benefits that, while are easy to quantify conceptually, are probably very difficult in practice, right? So people often talk about all the potential medical drugs that can be discovered in the Amazon rainforest. I think it's easy to quantify by just sort of saying, well, if you invent a new drug, you could sell that new drug for a certain amount of money, or that drug could basically, save a certain number of lives, and we'll quantify the number of lives coming up. But, how we could possibly predict how many drugs will exist in the rainforest, that's the far trickier question. And finally, you could think about even something as ephemeral as the night sky. We could think about how much are people willing to pay for a house where you could see the stars, where you could see the Milky Way. There's definitely something magical about seeing the Milky Way, as I remember sort of sitting in my car in Yellowstone National Park. And so the question is, if we could just see how much people are willing to pay for access to those, to see a beautiful sky, then that's another way economists use to quantify use values. Non-use values are we handle somewhat more straightforwardly, but sort of in a less satisfying way, right? Recall the non-use value is just basically the value of having that good or environmental benefit in existence just for the sake of being there. For example, what's the value of a pristine Arctic National Wildlife Refuge, right? If you don't recall, the Arctic National Wildlife Refuge is a refuge in Alaska, designed to sort of preserve the wildlife there that oil companies want to drill in. And so even though people may never visit, even though people may never sort of use that land, people like the idea of having it in a pristine condition. What about the value of a static climate? I'm not talking about all the use values of climate, of having a static climate, of sort of preserving our beaches, preserving our rainforests, preserving our climate, preserving our weather patterns as we know it. But what's just the non-use value, right? Just the idea of sort of the pure idea of keeping the Earth as we found it. How do we sort of think about that? How do we quantify that? What about the existence of a national park you would never visit, right? So on the previous slide, we talked about how you quantify the value you enjoy from visiting a park, but there's definitely parks out there, like there's this, George Bush created this national park in the middle of the ocean around Hawaii that chances are no one can actually get there, but it's a national park, and I think people are happy that it exists, but you'll never visit it, and so the question is, how do you quantify that happiness? And finally, perhaps, one of the most salient examples is, what's the value of preserving an animal from going extinct, right? There's tons of species of insects out there, insects, bears, birds that, that might go away. We may never see these animals. We may never we may never use them as for pets or for food, but somehow it makes us feel bad that these things go away, and that and so preserving them actually has value that we should sort of quantify when we do cost benefit analysis. So the standard way that economists use to sort of measure these things is something called contingent valuation, or in simple terms, just basically ask them, right? We just, there's a lot of, careful methodology for designing surveys, but we just ask, how much are you willing to pay to sort of keep the Arctic National Wildlife Refuge clean? How much would you be willing to pay to save panda bears? How much would you be willing to pay to save, I don't know, the spotted owl, right? And if we go to each person and we find that the average person is willing to pay, I don't know, $1 to save the spotted owl, and you basically add that up across all the people in the United States or all the people in the world, you get, if you focus in the United States, that's $300 million, and we say, okay, we should, as a society, the benefit to saving the spotted owl would be $300 million. However, Marty Weitzman, a Harvard environmental economist, has pointed out that there's perils to this approach, right? And one of the perils to this approach is that it's often sort of quite arbitrary, right? So, so Weitzman went and looked at all the money that, the United States spends on preserving endangered species, and they find that, what predicts the species that as a country we support is not how ecologically valuable they are. It's not how inherently important they are. It's pretty much how cute they are and how big they are, right? His term for this is charismatic megafauna, right? That basically, the Americans like spending money to protect cute and cuddly big animals, right? So, I mean, it's probably no surprise that, in general, we much prefer protecting, the cute, cuddly panda bear rather than the smallpox virus. And maybe that's fine, right? Maybe the benefit should be based just purely on the animals that we find cute and cuddly. But, it sort of shows that there's something arbitrary about, about this approach of just sort of going by people's gut feelings as opposed to going based upon some rational reasoning. The other problem is that people often really don't have a good sense of how much they're willing to pay. Right. If I ask you, would you be willing to protect the polar bear? You'll say, oh yeah, I'll pay $1 for that. And then I say, okay, what if I pick another animal? You say, okay, I'll pay $1 for that. And what about another animal? And you'll pay $1 for that. And pretty soon, if I just list enough animals, you might find yourself committing to say that I'm willing to pay. I'm sure I can list $1,000 or 1,000 animals or 10,000 animals on that might be endangered, and you pretty much find yourself committing to paying $10,000 to protect endangered species, which on the whole is not realistic if you take a step back, right? But just when I present you one cute and cuddly animal at a time, quickly adds up to quite a bit of money, and that people claim they value endangered species, but they may not actually place that same value on those endangered species. So just a quick summary of the different methodologies economists use to measure the benefits of environmental protection. Economists ideally prefer the revealed preference approach. The most direct application of this is basically just to look at market prices. How much you value for the candy bars, how much you're willing to pay for it. How much you value that national park is how much you're willing to pay to get in. All right, but when those are not available, then we could often apply to indirect costs. We look at sort of the travel costs of getting there. We look at hedonic values, which is like what I was saying about property prices. That basically people who buy property in neighborhoods by a polluting factory versus a non-polluting factory are we could compare the difference in prices to sort of get a sense of how much people value that pollution. Or how much money do people spend to avoid certain things, right? So if people spend a lot of money buying masks to avoid the pollution from nearby, then we could argue that the money people spend on masks is basically at least as high as the amount of pain or the amount of benefit they would get if we clean that pollution up. All right, so these are ideal because I think economists tend to believe people's actions much more than what they say. But if that's not available, then we turn to stated preference methods, which is just again, like I said, asking them how much they care, how much they value the life of a polar bear. The direct approach of just asking directly is known as contingent valuation. there are also various indirect methods where we sort of give people, various choices that they have to decide and trade-offs they have to make that might, sort of get a more accurate approach, though still not as ideal as sort of our direct methods where we actually have an actual price for these things. And believe it or not, measuring those attributes of environmental protection, the value of a park, the value of a polar bear, that's actually some of the easier questions in environmental cost-benefit analysis. Here are a few of the trickier questions. All right, the tricky issue number one is, what is the value of a life? Right, and let's just start with a question that sort of plagued philosophers for millennia. How much is a human life worth? All right, and the Economist answer for that is actually quite simple. According to Economist, a human life is worth about $8 million. And I don't mean that to be flip, right? But that's just sort of what current economic studies say a human life is worth to Americans anyways. People in other countries are probably worth different amounts, but this is the value the human government places on human life. You might wonder, how do economists calculate that? I think most people sort of assume that we calculate that based on your earnings potential, right? And I think that's the way that lawyers often use. Economists actually prefer a different one. All right, so if you think back when I said, what's the value of a human park? Well, the value of a human park is how much you're willing to pay for it. All right, so if you're willing to pay $20 for entrance fee to enter the park, then it stands to reason that you value that park at $20. Similarly, the value economists want to ascribe to human life is how much people are willing to pay to preserve their life. All right, and there's a whole number of ways of doing this, and the amazing thing is they all sort of give us the same answer. All right, so one way of doing this is pretty much to look at how much people are willing to pay for safety. So for a while back, before airbags were made mandatory, they were an option that you could buy, right? And so you could go to the car dealer, and there'd be some price, say $1,000 for airbags, and you would know that the airbags would reduce your chance of dying by some percent, and using that, doing some simple math, you could calculate how much people are willing to pay to save their life. All right. Similarly, you could think about jobs, right? So another place people looked for the value of human life is looking at different occupational choices. Many of you may not guess what's the most dangerous choice according to the census. The most dangerous occupation according to the census is maybe not what you'd expect. It's actually lumberjacks. All right, and I sometimes think that maybe we should have a holiday every year where we just sort of remember all the lumberjacks that have given their lives to bring us our paper. But it's definitely important, and people take the dangers of lumberjacking seriously. All right, and so and what studies have found by people like Kip Viscusi and others is that there are often different kinds of lumberjacking jobs, right? So say for example, there's one lumberjacking job that has a salary of say $30,000. All right. And say in this particular job, the chance of dying is 2 in 1,000. All right, and say there's another lumberjacking job, and the pay there is $22,000, and the chance of dying there is 1 in 1,000. All right, and so I'm not sure what the numbers actually were. These are just sort of hypothetical, but just based on these numbers alone, what you find is that lumberjacks, if these numbers are correct, are willing to sacrifice $8,000, right, 30,000 compared to 22,000, in order to reduce their chance of dying by 1 in 1,000. All right, and what that tells us is that the chance of reducing their chance of death by 1 in 1,000 times the value of their life is equal to $8,000, right? Or we could just sort of do some simple math, and that tells us that the value of a life to this lumberjack is equal to 8 million. All right, and it's just simple math just like this that economists have done across a whole wide variety of different contexts that tells us that people in general are willing to spend $8 million, to save their life. On average, statistically, right? It's not like people are, committing suicide for $8 million. It's that people are willing to reduce their chance of dying by, say, 1 in 1,000 for $8,000. And so as a policymaker, we should say, well, if people are willing to spend $8 million, that's exactly how much we should spend. Right? I mean, people often have this idea, and this was the Milton Friedman YouTube video I posted last time, that we should spend unlimited amounts of money for people's lives, right? We should spend 80 million, 800 million, that it's somehow inherently wrong to put any number on a human life. But the thing is that, economics is all about dealing with scarcity. We don't have the resources to put unlimited amounts of money on people's lives. We need a number, and the most sensible number for us to use is the number people are willing to pay themselves to save their own lives. And so, as a result, the federal government basically pretty much uses $8 million. Most economists sort of use $8 million. And I hope to convince you that this is a reasonable way of sort of valuing people's lives, because this is often going to be an essential part of our calculations as to what we as policymakers should be doing. A similar issue that came up while I was working at the White House was, how do we apply this analysis to animals? All right, there was a regulation that sort of came through. So part of my job at the White House was to help evaluate all regulations the federal government was doing that was related to energy and environmental issues. And the regulation that came through was basically concerned about right whales. Right, the right whale is a kind of endangered whale that's found in the waters in North America, and the concern was that ships coming in would had some chance of hitting the right whale. And that ships come, and that every time the whale was hit by a ship, they might die. All right, not always, but sometimes. And this happens once or twice a year. And so the worry, and so the response was that, in order to protect these whales from dying, we should put a speed limit. We should slow down every single ship coming into the United States, in order to protect these whales. All right, and in some sense, that's fine, right? These whales, have value, and we should worry about that. But there's a price to this, right? It's not free putting a speed limit. Slowing down all the ships means that goods and services that U.S. factories depend on, that U.S. jobs depend on, are going to get here slower. And if they get here slower, that basically means money. And and doing the math, basically on how much money is the U.S. economy losing to save each whale. The calculation from this regulation would basically put a price of several $100 million per whale saved. All right, and so it's interesting to compare that, implicitly, while regulations that the government passes to save human lives only spends $8 million to save a human life, inherently here this regulation is spending hundreds of millions of dollars to save whale lives. And you might, is this right? Is this wrong? It's hard to say. I mean, in some sense, it seems crazy to value a whale life above a human life. On the other hand, this whale is endangered, and so that every whale that dies brings us closer and closer to having this species of whale being gone forever. And so maybe we should be spending a lot more money to save these animals. But these are the issues that we sort of think about when we sort of tackle the costs and benefits of environmental protection. Another thorny issue when measuring the value of a life is how do we evaluate the life of a child versus the life of the elderly, right? So you might think, oh, every life is precious, and we basically should value them the same, and that's inherently what the federal government does, right? That if they're deciding between, say, building, I don't know, by locating a polluting source near a senior citizen home where two senior citizens' lives would be endangered, or by locating the pollution near a nursery where 2 baby lives would be endangered, the federal government by law has to sort of treat those lives exactly the same, and there's a nobility there. That sort of makes sense in a way that every human life is precious and every life should be treated equally. At the same time, you might also think that we should value them differently, right? That a baby has his whole life ahead of him, whereas a senior citizen may only have a few years left to live. So, so should we adjust for how many life years are left? Maybe yes, maybe no. And so, I mean, it's important to be aware of the implications of thinking about human life in this way. All right, I think it all sort of has a certain logical coherence, but we should be aware that it's not. It may have implications that we're not entirely comfortable with. One of Obama's and Clinton's economic advisors, Larry Summers, made this comment that says, "Oh, they're so poor in Sri Lanka, we should pretty much just, ship all our nuclear waste there because, they're happy to deal with it." Right? And in some sense, if we sort of think that Sri Lankans place a lower value in their life than Americans, that makes perfect economic sense. But it just sort of feels wrong, right? And he got in a lot of trouble for saying that. Similarly, if we think about all people value their lives the same, it makes sense though that people with different income levels may choose to make different trade-offs, right, between spending money on protecting their own life versus spending money on other things they need, like food or shelter. All right, and so this was sort of evident in Katrina, where you find that the hurricane hurt mostly poor neighborhoods. Right, and this wasn't because God was punishing poor people, as some crazy pundit said. Right, this was basically because poor people choose to live in neighborhoods where that were inherently more dangerous. Right, and they chose to live in neighborhoods that are inherently more dangerous because the prices are cheaper. So they are compensated for the danger. Right, they had to pay less money for their housing because they lived in a dangerous part of town, and this monetary trade-off between danger and life is something that goes on every day, everywhere in the market. It feels wrong. All right, and so while I said I still think cost-benefit analysis is the right way to sort of think about these problems, it does force us to consider some serious ethical dilemmas of the choices we're inherently making every day in society. Another tricky issue of cost-benefit analysis is when we talk about the benefit of $1, $1 here, $1 there. We haven't made a distinction as to a dollar to who. All right, and the relatively easier question to address is how do we value the dollar to, say, an American versus the value of a dollar to, say, a Bangladeshi? That's something that economists deal with pretty well. Right, so people often worry that cost-benefit analysis doesn't take inequality into account. Well, actually, I think it usually does. Right, when economists sort of do this, we recognize that $1 is worth a lot more to a poor person than a rich person. That if Bill Gates was walking down the street and stumbled across $1 million, that'd be worth very little to him. He wouldn't even have noticed because he makes $1 million, breathing every 5 minutes. But for most of us, if we bump into $1 million, it's worth a lot more. And so we basically sort of have a multiplier factor, right? Where we basically sort of talk about, we sort of estimate how much is a dollar worth to an American versus how much is a dollar worth to a Bangladeshi or Indian or South African or French or German or whatnot. And and we sort of and when we sort of evaluate the cost benefits, we sort of take into account how wealthy is that person in that country, so to make sure that the benefits that go to a Bangladeshi are worth a lot more than benefits that go to Americans, right? And that sort of advocates, that might advocate having us trade off, putting out some costs on Americans in favor of benefiting poorer countries. All right, and so economists in this sense are not as heartless as people sort of think we are. The trickier question, the one that economists actually really have no clue of yet as to how to resolve, is what's called sort of the delta debate, or how do we value the value of $1 to people today versus the value of $1 to people living 100 years from now. All right, and so in some sense, part of this debate was started recently by the Stern report. Nicholas Stern is a British economist who basically said that out of ethical fairness, we should value all people the same. It doesn't matter if they're living today. It doesn't matter if they're living in the future. It doesn't matter if they're living 200 years from now. All right, and well, ethically that sort of feels right. If you sort of think through the implications of what that means, it doesn't make sense at all. All right, so William Nordhaus, another famous environmental economist you'll hear about a lot throughout this course, pointed out that if you really believed, in Nicholas Stern's numbers, that means if the lives of the people in the future mean so much, we should be willing to sort of sacrifice everything today so our children are better off. Right? That it's in some sense selfish for us to be spending any money at all on ourselves. Because if we just sort of sacrifice everything we have and just give it and leave it to our children, our children are going to enjoy the fruits of those benefits for hundreds, thousands, millions of years. Whereas and so if we value their lives equally, then that's what we should be willing to do. And somehow that sort of feels wrong. Right, and the other reason why this sort of feels wrong is that our children are going to be richer than we are, right? I mean, despite the fact that growth is slowing down, it's still doubling every, say, 20 or 30 years, which basically means if we go to 100 years from now, our great-grandchildren are going to be roughly 10 times richer than we are today, right? So why should we be sacrificing money today in order to make our great-grandkids feel better, better off, because they're going to be so much richer than we are. They'll be richer, they'll be more equipped to deal with the problems. Why don't we have them sort of subsidize us, because they're relatively better off, because we create the economy to provide for them. And so the number that economists use to sort of measure this, to measure how much we should trade off values today versus values of the future, is known as delta. And this is sort of a thorny issue that economists still haven't fully resolved how to deal with. The final tricky issue is understanding what is the value of a gamble, right? How do we deal with risk? So economists actually have a long-developed tradition, going back 100 years, of sort of thinking about risk. We sort of take the probabilistic view on the whole and think about expected values and expected utility. It's important to point out that these two things are not necessarily the same, right? That say imagine you earn $50,000 a year, and you want to compare either a 50% chance of losing $1,000 or a 1% chance of losing $50,000. All right, and you want to say which one would you prefer? And of course, I think most people would sort of prefer the first, right? So the expected value of these two things are both the same, right? The expected value of both is equal to $500, right? But the expected utility is quite different, right? Because losing $1,000 is painful, but losing $50,000 or all your income for the year is very, very painful. And so this is especially relevant when thinking about environmental issues, because oftentimes what we're talking about is not it's not small losses. It's not like a 1 or 2% loss. What we're really worried about is the tiny percent chance of losing everything, right? The tiny percent chance that that we have sort of major changes that sort of make human living unbearable somehow. All right, and the harder problem there is that we don't even know what these percentages are, right? We don't know if it's 1% or 0.1% or 2% or 3%. The scientists have a pretty good answer as to what the average effect is of climate change. I think our knowledge there is pretty clear, but it's the percent probability of a catastrophic change that we haven't been able to pin down, right? Where 1% probability versus a 2% probability, while only a 1% difference has huge effects as to how we should how we should respond and how should we behave. A related issue when sort of thinking about how we should deal with gambles is what's sort of known as real option analysis. All right, so a lot of you probably have heard of stock options as something that companies give, but probably a lot of people haven't really thought about exactly what a stock option actually is. And what a stock option actually is basically it's the value of waiting and seeing is what I call it, right? It's basically the idea that, well, I don't, is the idea. Yes, I could choose either to buy the stock today, or it's even better is I could choose to wait and see and decide to buy the stock later, right? A stock option is the option to buy sometime between now and the future. And and what's nice about option analysis is that we actually have really good financial models, right? Sort of Black-Scholes models and things that allows us to quantify pretty precisely what the value is of waiting and seeing. This is going to be important when we think about environmental policy, because there's a lot we don't know yet about what we should do with the environment. I think economists are almost all agree that we should do something. What we don't agree on necessarily is when we should do it. All right, because we could either do it now, where it's going to be expensive and there's a lot of uncertainty, or we could wait and see, right, and do it in the future, where our kids are going to be richer, they'll be better equipped to handle it, they'll have better technology, they'll have less uncertainty. All right, and sort of how you weigh doing it now versus doing it in the future is going to depend a lot on sort of the value of the option. All right, so I've talked a lot about sort of thinking about the benefits of environmental protection. The flip side of the coin is how do we think about the costs of environmental protection? All right, and here economists, don't have as much to say. One way economists are thinking about the cost is basically, well, we just do surveys, right? Just like for the benefits, we ask them. For the cost side, we also sort of ask them, and we say, okay, well, how much will it cost you to sort of build, something to reduce emissions? Or how much will it cost you to build, not in the endangered wetland, but in some other piece of land, right? And so this is one way to do it.
Another way is just the engineering approach, where you basically go to engineers and say, okay, well, what are the various technologies you would need to sort of achieve this environmental protection? What would you have to build to sort of reduce the emissions? What would you have to build to sort of protect this polar bear habitat? Ask the engineers to sort of come up with their best estimates for how much it would cost and go about it that way. And then the third way is basically just to look at supply and demand estimates, right? Just look at the market. Look at how much, compare how much it costs to sort of buy electricity that's clean versus buy electricity that's dirty, and sort of use that to sort of get an estimate of how much it costs to produce clean electricity. And I think this is the ideal approach, because surveys and sort of engineering estimates are always fraught with error. People often will overstate or understate based on their own prejudices. But the market really basically says that, well, people are putting their own money on the line. And so just like on the benefit side, where we prefer to sort of see how much people are willing to pay, actually for these environmental benefits, it's also useful on the cost side to see how much are people willing to pay actually for these environmental protection technologies.